Hey, sounds good. Yeah.
Keep it that close. Okay. I ran to get lunch. I didn't have time to eat it. So I'll just escape for about 15 minutes so I can eat my lunch. And I'll be back for the Q&A.
Okay.
And you don't need, do you need an introduction?
No, I'm
No,
okay.
no, you can take it.
Like
Good, good. So just, I'll stay here until you start. And then when you see me leave, don't panic. I'll be right back.
okay, thanks.
Good. And this is for questions.
Okay,
It's yours.
thanks. Okay.
Check, check. 1, 2, 1, 2. Hey, hey. Flip it, wait a couple seconds, and then you're hot. And then when you're done.
Is it on? Awesome. Thanks so much for coming. Hope you're having a great day. Second day here. So I'm Thomas, coming from Harvard Medical School. I did my PhD in Geneva in genetics. I've been with Harvard Medical for 2 years, doing mainly hospital data analysis with a focus on NLP. I presented something last year here, semantic search, and I was talking about how hallucinations make it hard for researchers to work with LLMs. And now we're starting to have some projects where we're integrating it really in our pipelines. So hope you're going to be interested. I do use a bit of a lax definition of agents, first of all. We're not going to talk about LLM planning, orchestration, MCP. For here, what we mean of agents is integrating it in pipelines. So we'll have pre-processing and post-processing. What we really want to do is automate some high research impact tasks. We want reproducible frameworks that the clinician can understand and go into the details for when we want to make sure that the model is doing it in the right way. So I'll be presenting two main projects we've been doing, and there's some key steps, some similarities, and I think this is the really interesting part is out of all these LLM projects, what are the things that we always need to do, and how can we build some software that makes our life easier for every task but remains general enough. So I'll start with introducing a bit the problematic. So in research studies in hospital, we mainly have two kinds of data. We have the very codified, structured data, and the notes, comments from clinicians. So in the very well-structured, you will have diagnoses, medications prescribed, the labs and procedure performed, the results from them. And in the notes, you'll have reports, justifications of why a medication was prescribed, why a diagnosis was performed. You will often have in these notes, oh, I'm suspecting this disease. The patient needs to follow up with this specialist. And so it doesn't mean that the patient has the diagnosis, of course. It's just a lead to build on to. And we see this problematic also in the codified data. So if you get a lab for testing your blood sugar, maybe the clinician suspects that you have diabetes, and you might have that in the codified data. So this is one of the pitfalls of the codified data that we address by having a look into the notes. If you have a look at papers of hospital research studies, you will often see how they define their cohort will be, I want patients with at least 2 diagnoses of this code, or 1 diagnosis and the usual medications prescribed. So there's usually a way to make sure that your patient cohort is, really has the disease. So yeah, this is what I'm telling here. And one of the things in our lab we develop is phenotyping algorithms. So here I'm explaining to be able to do a bit more accurate patient cohorts, instead of just doing, okay, 1 diagnosis code plus 1 prescription, we can have a look at the usual labs, the usual medical concepts mentioned in the notes, and we do a covariance based on this, and so we're able to do it a bit more in a more sophisticated way than just 2 diagnoses or 1 prescription. And to be able to measure these covariance-based methods, we do chart review. So we'll actually go into the patient notes, say as a gold label, did this patient really have the diagnosis or not? This enables us to say our algorithm has 90–95% accuracy, and then once we did this, we manually checked it on 100 patients, we scale it up to 10,000. So this is one of the usual case of chart review that we perform. And so more on agents, how we're using agents on the nodes two projects that my lab has worked on, medication history. So similarly as diagnosis, sometimes we have it in the code, but it didn't actually happen. In medications, it's similar. You might have insurance denial, maybe you didn't receive the medication. These will be information that you will have in the notes. Usually the clinician will say, well, he didn't really start that. And so we're using LLMs to enhance the codified data on medications. And we also did one for heart failure phenotyping because it's an important contraindication in rheumatoid arthritis medications. So it's a key question for us. So now I'm gonna start introducing the projects we're gonna talk about in this hour. The first one is on inflammatory bowel disease, so Crohn's disease, ulcerative colitis. So the usual process will be that the patient will have a colonoscopy, and in the report, if it's all okay, you might have the clinician who says bowel preparation was fine, the colon is all good, and if you have moderate disease, you might have there was some ulcers in these regions, this region was inflamed, there was some polyps that were biopsied and were awaiting results. This is the typical report of a colonoscopy. And these can be useful to measure treatment efficacy. So let's say a patient has a moderate disease, starts taking treatment, then 1 year later he comes back, does the colonoscopy. Does he have mild or severe disease? And if he has mild, is that treatment worked? And severe, it did not. So this is the usual way to measure treatment efficacy that you will see in papers. And it is done manually by the clinicians. They will go over the report. They might have 300 sample size, so 300 patients, more or less. This is the usual treatment efficacy studies you will see in literature. So we're trying here to use the previously collected labels as our ground truths, train our agent on it, and then be able to apply it on a much larger scale on the full hospital. So from around 500, 1,000 patients, we go to 15,000, 20,000 patients. The second project, so I'm working on suicide prevention. One key challenge in there is the codes are notoriously challenging. One example is that the patient will come into the emergency department, has some injuries. The nurse will put them down and say, oh, well, maybe he needs to go to psychiatry. But then it's actually the psychiatrist who will make the diagnosis, this was a suicide attempt. And this is one of the reasons why we often don't see in the EHR codified data those codes that we are very interested in. And it's already a low rate event, it's rare, but even more we have missing codes. So what's actually happening is that we're including much broader codes, like broad injury codes, to make sure we capture a bit more, even if it means much more false positives. So this is something that is always done in the current studies in suicide prevention. And so we're hoping that our agents can enable to diagnose these, to identify when it happened more accurately than the codified. Another interesting point is that here we're looking at an exact date also. We're not just diagnosing, we want to know the exact date of the event because we usually want to put it in a survival analysis. So described a bit the overall problematic. We can start getting into the more agent think part of it. So why I didn't go with the usual agent definition that you will hear around here is that it leaves too much liberty to the LLMs, and we want to make sure that it respects our medical guidelines. It doesn't plan too much on its own. Some example of the limitations I saw was, so in IBD and colonoscopy, one thing you can see is the patient comes in, he didn't prepare well, he didn't do like the, often the patient needs to not eat for like 1 or 2 days. If he didn't do that, the report of the colonoscopy might say it was not feasible, so we're reporting it to the next week. He comes back next week, then you have it. So here you have 2 notes. So how do you process that? Do you put them all together in one prompt? If you do that, and you just ask the LLM to identify the date by itself, I was quite surprised, but the LLM often gets it wrong. Like, I get some dates, no colonoscopy attached to it. So this is one example where I don't want to leave this to the LLM. I want to keep tracking it myself. Another example of issue I was facing in suicide prevention. So there's a lot of subtleties in, there might be patients thinking about it, planning it. You might have self-injuries that are like just superficial self-injuries. And so trying to explain this in a prompt to the LLM is, he will get it wrong most of the time. One example is if he has superficial cuts and is thinking about it, then he will say, oh, that was a suicide attempt, but actually no. So to define these, it's important to have the clinicians that support you to make sure you're interpreting the clinical definition correctly. But so even for you as a data analyst with expert support, it's hard to understand. So for the LLMs, it's going off track completely. So here I want to pause on traceable AI, because it's not only about explainability and not even about reproducibility. Often what the clinicians will ask us is, show me the exact note that is supporting what you're saying. So you're saying that this patient had a suicide attempt at this date. Show me exactly. I want to double check it. We can also think about cutoff values, overfitting problematics. So we want to have a traceable pipeline where we can come back and say, this is why we made the decision. I think that explainable often just says these features contribute, but not necessarily what are the interactions between them. So this is how I feel there's a difference between traceable and explainable and reproducible. So here I'm starting with the example that I was mentioning. If we put several reports in one prompt, the LLM will not get it right. But we have to admit that it's doing a very good job on identifying the natural language parts. So mild disease, we can scale it to 1. Small ulcers, it will understand it's mild. So we need to leverage what we can and track as most as we can with the classic methods. So this is why I'm integrating it into a larger pipeline with an extensive pre and an extensive post processing steps. So safety alignment is also a big question, especially in suicide prevention. Last year I was mentioning that I was getting often safety errors when I was asking him to map suicide relevant features. So this does make it even harder to use commercial models because commercial models might have additional guardrails than local models. This is arguable, but it is something you will need to keep in mind. There will be some things that the LLM refuses to do. I saw this morning the Hollywood special effects talk. They were saying that when you're manipulating a video, if the guy has a gun in it, the LLM will refuse to do it. So this is another example of a safety. So I saw that this was a good moment to introduce my team. So Tianchi is my professor. We have Katrin that is in the rheumatology at the hospital. Ashwin, who is in gastroenterology. William, psychiatrist and researcher. And Huayuan is a PhD student in LLM and gave me quite some good insights in reasoning models that I will mention a bit further on. So we described a bit what we wanted to do, the chart review, the usual problems with agents. So now we can start thinking about how are we going to actually implement this. So this figure will probably be in a similar form in a paper quite soon. So in this one, I did it for the gastroenterology project. We have the first step, basic, select the nodes, build the prompts for each date. So we're keeping track of the date. We want to make sure each prompt corresponds to one patient and date. We're calling OpenAI GPT-5, parallel requests. Then we parse the responses. So we ask to output the JSON format. We convert this to CSV. We might have some request errors. We recall this sequentially to make sure it's not about token quota issues. Then the normalizing response is a big part that I'll come back on. And then we have a final rule-based medical inference. So now I'm going to detail a bit each of these steps. And so first of all, a little reminder on just setting clearly the specs. Preferably, we call it on individual nodes because we're able to keep dates. However, you might have too many nodes, too many patients. In that case, you might want to do just extracts, but you still need to call it individually on each patient to make sure you can come back to something. Here I'm giving some numbers. So in the suicide prevention project, our ultimate long-term goal is detecting, based on the nodes, every event over the lifetime. And the number of patients we're trying to scale to is around 1 million. And in this project, I was doing 1 year for 3,000 patients. So starting smaller, 1 year is defined because it's the 1 year post admission to a psychiatric hospital. So for one patient, 20 nodes on average, and each node might be 10,000 characters long on average. So we're asking the LLM to output the information as a JSON to be able to parse it. To perform this, there's actually quite little models that will enable you to do this correctly. I did a few tests. There was some prior publications on Mistral OpenOrca 7B. However, I really wasn't able to get satisfying results out of it. I think maybe because I'm asking quite a few, I'm asking maybe 20 fields. So in the previous papers, maybe it was much smaller. From what I saw, only GPT-OSS and Chiwen, the parent model of DeepSeek, were able to output JSON consistently. You might want to try Llama 70B, but so outputting JSON was our core requirement. A few other considerations: context window. So I was saying a node can be around 10,000 character long. You will need something that takes this easily. I think that DeepSeek, the not too big models, has quite a small context window compared to GPT-OSS. So that was my my reason to move to GPT-OSS. The larger DeepSeek model and Chiwen, like 600B, are able to have similar context window as GPT-OSS, but the like medium size around 100B will be quite limited. GPU requirements, of course, and the country of origin can be quite important as you're deploying it in compliance environments. It might also influence safety alignment. So this is just some things to keep in mind. I can't really say, I don't have big numbers on this, but it's just something to keep in mind. Yeah, GPT-OSS 20B fits on a 50 gigabyte GPU. You will need to think that your context window does take quite some impact on your RAM, so you can just barely fit it. And 120B on 2 GPUs should be fine. And for commercial models, so Azure has HIPAA compliance, and so this will be something you will need for medical applications. So in these projects, the gastroenterology one, I'm doing it with OpenAI, and the suicide prevention one, I'm doing it with GPT-OSS 120B. Then to actually run these models, you have 3 main choices: Olama, VLLM, SGLang. I started out with Solama, but to do inference on thousands of prompts, VLLM really outperforms it. I haven't tried out SGLang for the moment. I hear that it's better on multi-GPU settings. So a little background on reasoning models. So we had large language models, let's say Llama 7B, and 1 or 2 years ago, one of the big hot things was chain of thought, and this enabled the LLMs to get much more accurate. How it's performed is you basically have the same under first layer of transformers, but then you're fine-tuning your model to describe precisely the steps it takes to get to the answer. So this is chain of thought, and by extension, reasoning models. this is much better, but it is also computationally much more intensive. So depending on your task, you might also just stick with a non-reasoning model, as it will be much faster. It does changes a few other things. You don't have a temperature parameter anymore. In some models, you might have minimal to maximal reasoning. So 7B is not a reasoning model. Mistral Open Orca was some early prototypes of a reasoning model. And so in the commercial models landscape, GPT-4o, for example, is not a reasoning model. It will be much faster. GPT-5 Mini is, and you can have several levels of reasoning, 3. And I think that GPT-OSS, you should be able to specify the reasoning level, but I think I remember that VLLM was explicitly saying that it's not supported, so you just have default for the moment, medium. And so I was saying that you might want to do non-reasoning models for some tasks. And it does highlight that often when we talk about AI, we talk about reasoning, so calculations but for me, the LLMs are also very useful just as NLP tools. When I'm doing mild or moderate disease maps to 1, it's I would say it's a bit arguable. Of course, the border is hard to put, but the point I'm making is that you can do some AI projects with a little input, and that's what I call reasoning heavy. You don't have much things to explore, and you can do NLP projects with so a huge amount of input, and then you're rather in the NLP domain. You're rather trying to extract some concepts that you'll further pre-process, post-process. So I do kind of like to distinguish the reasoning heavy, the more usual AI, what we think about, and the still relevant NLP tasks of identifying concepts and doing more of the reasoning yourself in your pipelines and your algorithms. So that was for the concepts. Now we have a bit of all our tools. We're ready to get the hands dirty. So coming back, I was saying select nodes. So input selection. One of the key part here, retrieval augmented generation. So you have large inputs. They are chunked. You store them with embedding models. When the user inputs a query, you retrieve the most similar chunks. So if you have 1 year of nodes of patients, you can just select a few and just feed that to the LLM. If you feed everything, you won't be able to scale. I'm moving towards a second way, not just semantic similarity, but also merging lexical similarity. So hybrid search. This can be exact or approximate string matches. It's very, is the kind of the old way of doing search. But it is useful to address the limitations of embeddings. One example of embedding limitation I'm seeing is for the LLM and the embedding models, suicide attempt is really a psychiatric disorder. So it will be very close to psychosis, hallucinations, and maybe if you have something in the note like cut himself, he will rather classify that as a small injury, and you might not have it very similar to suicide attempt. So that's one example of the limitations of embeddings. And another important thing is when the maybe it's rare term that doesn't have much semantic meaning. So this is where lexical and hybrid search helps you a lot. I performed this with OpenSearch, fork of Elasticsearch. There's a few other talks these days on OpenSearch. Some usual software to do these are Milvus and Chroma. There was a nice a talk talking about comparing the performances between all these different choices. For me, it's also that OpenSearch can do hybrid search out of the box, whereas with Milvus and Chroma, you would need a second system to combine them. So that's ease of use for me. This was my little test ground for hybrid search. I started out with 350,000 abstracts of papers. So in abstracts, you might have 20 sentences. I chunked them by 3 sentences. In final, I have something like 2 million chunks. I embed these with BGE. It's an embedding model with 1,000 dimension. And my little API is you put in a query. Here the query is BLK gene. And here is the output. So you have the article to the PubMed application and the little chunk that had the highest similarity. And in this case, the 2 first hits were actually from the same article. So this was input selection. Now we're moving on to building prompts. So the basics, you describe your goal and task, your expected output, you give a few input and or output examples, especially outputs. And once you did a few runs, you might want to integrate additional considerations of errors that you noticed. There are some little tweaks around this. A famous one is, if you do it correctly, I will tip you $1,000. I saw another one earlier where it was saying, your mother has cancer, you need money. Personally, I don't do this, but I do use repeating some instructions. It doesn't necessarily work. I have some examples of a friend that was even like writing it 20 times, do not take into account this, and still ignoring it. I try to just repeat a few times, you should not take this into account, this contributes 0. This is a nice moment to introduce DSPy. Maybe show of hands, anyone heard of DSPy? 1, 2. So DSPy tries to abstract out this prompt engineering. So let's give an example. You have some input emails you want to classify high, low priority. You have 100 emails. You give him 100 labels. This one is high, this one is low. And so DSPy will try to make up a prompt on itself to classify correctly. You don't even need to give him a seed. You don't even need to ask him to output something that is human readable. But you can, if you want, you can start with a seed and you can ask him a readable output. Yeah, I haven't tested it yet. I'm thinking that for medical considerations, it might overfit. So yeah, I don't want it to just focus well on my few 1,000 cases when I'm gonna scale it to 20,000 patients. I want to try to keep some human/medical reasoning behind. So once you have a prompt, you're ready to call your LLM. I'm using VLLM, I was mentioning. We start by initiating our endpoint. I'm using Podman. It's a rootless Docker. It's good for shared environments. In this little snippet, I'm using 4 GPUs, GPT 120B, deploying it on port 9010. The no enable prefix catching might save you some time. I won't elaborate too much on this, but we can come back in the question. And yeah, 0.15 Docker image, and we cage the model to make sure we don't download it each time. So now our VLLM is running on 9010, and we can call it with any post query. I'm using R. This is the example of how I build my query. I have a function with my prompt coming in, and this I build my body, retrieve the result, and get it back from the function. So we waited a few days, a few hours. We got the LLM output back for all our inputs. We have our JSON objects, and now I think it's the interesting part of normalization. So one of the things I saw was I was asking him, if you have ulcers, you put one in with the field name of ulcers. And 20% of the time, it will work 80%, but 20% of the time it will tell you presence of ulcers equal 1. So when you're trying to put that as a final CSV, it will break your thing. And so you have maybe 5, 10 fields you want to identify. So you have some randomness that you need to take into account. You need to have an automated system that will map them correctly to the box you were expecting. You could just recall the LLM, but it would be quite a lot of calls. And most likely you will need, in any case, one mapping at the end. So I was doing it with string distance, regex, but one of the things is that at the beginning I was doing it like on 100 patients. I still had some labels I hadn't looked at. When I scale it to 1,000, oh, there's some new cases that I didn't manage. Is it still going to work when I'm going to do it on 20,000? So I think that here, this morning, the concept introduced was human on the loop. It's not necessarily in the loop in the sense of we're not waiting for a human to say yes or no, but we do need a human to go over some of the logs. So one of the questions is, how do you make logs that you will be able to review easily? So this is my traceable mapping table. In the columns, you have the 5 boxes I want to get to. And in the rows, you have what was actually returned by the LLM. So in here, it's like on 100 cases. It's not that much. In the next slide, we'll see a bit more. But we already have some examples in the second part, narrowings, example stenosis, narrowing stenosis, surface disease, surface involved by disease. So these two should map together. And so I'm doing little regex plus string distance matching. And I'm double checking that, okay, these 3 first, they correctly went into narrowings. These 2, they correctly went into surface disease. These 2 went into surface ulcers. So that's how I'm doing the human on the loop, the traceable mapping. And so when we go to 20K, this is what it looks like. So you you can't be able to think about every case that's going to happen. You need to just try it out. But I was lucky. From my 1,000 to 20,000, I didn't need to change anything. It's more when I was doing the 100 to 1,000 that I needed to review some of my code. So here in the first 4, we can see there was 2,000 that was actually the correct field from the beginning, but almost 1,000 that were not. So if you're recalling that much, it makes a lot of further calls. So I think that you shouldn't just like recall 30% of your prompts. You should rather find good mappings. So now you have your nice CSV. That was I think the main conceptual part that I found interesting. Then we have a bit more medical intelligence. Maybe you were asking about ulcers. A second field is surface affected. The LLM told you, yes, there's ulcers, but it didn't tell you about the surface. So I'm adding some little rules. If you had one here, you will need at least one here. A last part, uncertainty and estimation. So it is inherent in the domain. The clinician might say, yeah, it's a bit in between. So you need to have a system that can manage this, and in your evaluation, it's good to take this into account to not underestimate too much your performance. How I started doing this was 3 independent prompts: low, average, high estimate. So let's say the node says mild or moderate. In the low one, you would take mild, in the high one, you would take moderate. In the average, you put 1.5. So in the first case, I was doing independent calls. The nice thing is that you can see some randomness in the LLM. Like you might ask him for the low and the high will actually be lower than the low. However, this does increase by 3 times the number of prompts you need to make. So in our scalable version, we're just doing it in 1 prompt, asking for 3 estimates. But on our, like, if we want to really focus on 100 patients, we can do three calls independent. Then once I have these estimates, if they all agree we're good, if they don't agree, I'm flagging it. It might go for manual review by the clinician. It's usually like 10%. So here we're a bit coming to the end. This should be clear by now if you have more questions about it. So build the prompts, call in parallel, pause the response, normalize, rule-based medical inference. The cool applications of this: treatment efficacy measurements on much larger populations. So we performed it for around $300 on 50,000 nodes. This was with the OpenAI GPT-5. If you don't really have GPUs, I recommend it because it will be easier to get you started. However, if you want to move in a more intensive, it might be worthwhile to invest in the GPUs. Maybe a box, you can count around $50,000 to get a box. So treatment efficacy in inflammatory bowel disease and for suicide prevention, increasing the reliability of the codified data. Uh, the core experiments I did previously, 2 or 3 days with 4 GPUs to do 1 year of notes for 3,000 patients. We were estimating to reproduce it on the Google Compute would be likely around $2,000. And we're now working on scaling this to get to something that we can run on 1 million patients on their lifetime. So here, what I was saying on 2, 3 days, I was doing every note, full notes. And now we're trying to do just extracts, just the notes that are interesting, the psychiatry notes. And this is where hybrid search comes into play. So the GPUs were kindly offered by the Center for Suicide Research and Prevention, collaboration between Mass General Brigham and Harvard. You have Jordan Smaller over here in the middle, and my professor is over here in yellow. Some cool ideas I'm working on currently. So when I'm doing note selection for the case of 1 million patient over lifetime, currently I'm doing some heuristics to narrow down on the notes of interest. We have too much notes to process them all, even by just selecting extracts. I'm thinking that maybe agent could help me in there to focus on what is the time period that I should focus on.
Sorry, I didn't see it.
So currently I'm doing simple heuristics. Maybe the agents could help me increase performance. And the really cool, more long shot project I'm thinking about is, so for prediction of mental health disorders, DSM-5 has some questionnaires to evaluate personality traits. So personality traits can be measured in various ways. Facebook models you by your likes. The usual model you might hear about is Ocean. You have like openness, extroversion, neuroticism. Each of these are usually linked to one mental health disorder. So it's like, if you're very neurotic, you might be schizophrenia down the road. Autism has a bit of links with obsessive compulsive disorder. Bipolar has some links with impulsivity. So they are quite relevant in the medical domain as well. DSM has a list of 200 questions, and then they say, okay, if you answered in this question, this goes to this personality trait, you sum them up together. The guideline is that the clinician should ask the patient to do it every 6 months over 2 years, and if it's consistently high in one personality trait, then we might want to investigate. Maybe the patient doesn't have a formal disorder, but some problematic personality traits. So this is how DSM suggests to use it. And how I'm thinking of using it is trying to answer these questions based on the notes. So let's say one of the questions is, I'm a risk taker. This gets mapped to impulsivity. In the notes, you might have various things like the patient ran away from home, he's a kid, he's in conflict with his boyfriend. Here the example I'm saying is jumped over a fire pit at a party. You could think it's like not very relevant, but it can maybe help you answer the question of, I am a risk taker. And so I'm thinking that this could be a cool way to model personality traits based on notes and try to predict better mental health disorders with that. Thanks a lot. Any questions?
Yes. There you go.
I have a couple questions, but I'll start with this one. You mentioned chunking based on an arbitrary sounding 3 sentences or 2 sentences. Does chunking have to be done blind like that, or naively? Or can you use an LLM to sort of chunk for you based on thoughts, or concepts?
It makes me think of, I think, contextual retrieval, where you're using a chunk, but you're also asking the LLM to summarize a bit the chunk above and the chunk below. However, one thing maybe you need to keep in mind is that we're doing chunking for the retrieval augmented generation, because the retrieval augmented generation, like the RAG, the embedding part, is more computationally efficient than calling the LLM. So I think here we're trying to do this to not have to call the LLM on everything. So it's not really the goal to call the LLM to help us on the chunking, because it's computationally expensive.
Hi, my question is, with reference to neurology and depression, connecting to suicidal tendencies. I attended a session on deep brain stimulation, where they are able to detect depression and also to treat it. That means that they are able to read brain signals and infer that there is a cause for severe depression. My question is, can such information be combined with your AI efforts and conclude to a more concrete decisions and conclusions?
Yeah, I would say these sort of signals are very real time, and my signals are a bit more long term. So definitely can be used together. It does make me think of maybe when you are able to measure depression, let's say you're already a bit in the zone of not acting a lot, maybe staying in bed, and maybe the important part, at least for me, is how to intervene before you get into the zone. So I'm just maybe that's one limitation of the brain-computer interface.
You mentioned more legacy LLMs and then now reasoning LLMs. Are reasoning LLMs runnable locally, or if you want to use a reasoning LLM, are you forced to use an API?
No, the OSS, GPT OSS are both reasoning models.
And it works with a llama or VLLM?
Yeah.
Questions, anybody? More questions? Yes, back there. Okay, there we go.
For these notes or the charts, how varied is the language? Like, do you really need large language models, or can you constrain what it needs to look through a small language model or something specific to just this area of exploration, and then not have to worry about others? The reason I'm thinking is maybe you have a small language model for the IBD and another one for something else. Would they encompass enough information to give you results?
So should we use rather 2 different small language or 1 large? From what I see, you do need a lot of general knowledge. So I'm a bit afraid that the smaller don't have that. In the IBD project, it's probably not a big deal. You might be able, because you mainly rely on a few synonyms like stenosis, that means narrowing. That's important that your language model knows about that. Other than a few synonyms like this, you don't need that much reasoning. In the suicide prevention, however, the so I'm there's also like very various cases that you will come up into the notes, and I'm a bit afraid that if you fine tune too much on one case, you might lose the generalizability. I do agree that it could be cool to measure the difference, because you would probably get much more computationally efficient. So that's the really key thing that would make you want to go into that direction. So it could be cool to compare either a RAG with GPT-120B or a small language model, and you don't need a RAG. So I think that would be relevant to test.
Any more questions? Questions? Well, thank you. Excellent questions, excellent presentation. Thank you very much.
Thanks all.
Yes, it all worked. use this microphone and test it.
Hello?
So
Hello?
you have to hold it that close.
Hello?
Yeah,
Hello?
that's good.
Okay, cool. That's good. Okay. Thank you.
We use this one for questions.
Okay, great, great.
And somebody should help you plug in, I guess. How to plug his computer.
What's up?
I'm just, I don't
Okay.
I don't know. I was just getting him to test the
Okay.
microphone.
Do you want to use the headset, or is this working? Just so you don't have to hold it.
This one.
No, they've held it. They've held it.
They can, but I'm saying if you don't want to, you can use the headset.
Oh, okay.
Yeah, maybe this is.
Yeah. So all you need to do is turn it on, and that's it. So there's no settings. Yeah, and you can throw it in a pocket or whatever. It's whatever your preference is. But yeah, these are. So it goes like that.
Oh, the headset's new for us, yeah. They've been just using a microphone. But anyway, whatever you like.
Well, if any of the speakers do want to do it, you can go behind the ear. Over your head, behind your ears. And then you can just arrange that wherever it's go.
Hello?
You don't need this.
Okay.
Turn this way. So let's get that. Okay. There you go. Okay, try that.
Hello? Oh,
Does that sound good out there?
okay. Okay, way to connect.
You can turn that off until you're ready. So you don't have to have everybody listening to you getting ready.
Yeah.
Just the switch on top.
There you go.
You like that one or this one? Because you can choose. All the other speakers are for sale. There's an online I don't know how to do that. Oh.
Hello, can you hear me okay? Okay. Yeah. Thank you very much for attending to my talk today. I'm happy to have opportunity to present to the SCaLE. With this my third time attending this conference. I'm happy to have the opportunity to present our work at the Children's Hospital Los Angeles. So a little thing about myself. I work in the Children's Hospital Los Angeles. I work in a genetic testing center, molecular diagnosis, tumor test, genetic disease test. So we process a lot of genome clinical sequencing data, also clinical data in our daily work. So that's why I'm talking about our experience with AR tools in these applications. So my talk, the topic is 1,000,000-to-1 and word-to terms, the generative AI tools in action for rare disease diagnosis and patient data harmonization. So I've introduced two generative AI-based frameworks and the practice we use in our work, and addressing the two challenges in the precision medicine for the data science part. The first one, 1,000,000-to-1 challenge, means we need to, in genetic testing, we need to filter millions of variants into a single causative variant for a patient, and then generate a diagnosis report. The second part is the word-to-terms challenge, which is about transforming the unstructured clinical data into the ontologies and dictionaries. So the first part is about the 1,000,000-to-1 in the genetic testing data processing. We are trying to filter the millions of variants from patients and generate a diagnosis report. So precision medicine, which was really get hot in 2015, it was the first well-known as the molecular diagnosis. At that time, the President Obama proposed the precision medicine, give promise that patient can get a diagnosis and which will direct the treatment and get the treatment affordable and precise. So usually the genetic molecular diagnosis start at the clinical lab where they do the next generation sequencing data. This kind of lab in the US will be SCaLE certified and also kept certificate at least to be able to offer these tests to patients. Then followed by the data processing, including the variant calling and the interpretation for the pathogenicity, and finally sign the molecular diagnosis report. Now the beauty reality is that we can get $100 genome sequencing. The technology is very much better and faster and very cheap in the clinical sequencing. The clinical sequencing have two types of sequencing. First is the next generation sequencing, which was short read, mainly provided by Illumina sequencer, complex genomics, Artima, and now the Rush, they have a new sequencer. So basically, most of the companies, they are now claiming that they can offer the whole genome sequencing at $100 or a little over $100 per patient per human genome. For some patients, if the next generation sequencing data was not positive, they may need to go to the third generation sequencing using the long-read technology from nano per pegabile, which will detect some disease-causing mutations that are missed by the next generation sequencing technology. And so this graph left side shows the cost, how the cost was coming down from over $10 million in the 2021, the earlier the start of this century, And after the 2007, we get the next-generation sequencer from Illumina. The per genome costs are going down rapidly. And now, actually, this last year, people already are offering $100 whole genome sequencing. And with the new sequencer to the right side, the high throughput in the Illumina, they can generate 8,000 gigabyte data a day. So basically, yeah, this is the general flow for the clinical sequencing in the molecular diagnosis service. First, the SCaLE certified lab will do the genome sequencing to generate a whole genome sequence or whole exome sequencing. If the whole genome sequencing WGS, you will get 50 gigabases of data. Then the secondary analysis will call the variants which are changed in the patient against the reference genome. And this will return you 4 to 5 million variants if you are running whole genome sequencing. After whole genome sequencing, we have a tertiary analysis that where you are trying to filter down from the millions of variants and identify one causative variant for the disease, for the clinical phenotype in the patient. That's why I call it the millions to one. Actually, in reality, the diagnosis rate is only 25%, at most 50%. That means that you, in the lab, they will call over 10 million variants and finally get one causative variant call to the patient. So it's actually 10 million to one at least. So the challenge in the precision medicine for the diagnosis is now come to the ugly side that we can generate data very quickly, rapidly, but we lack a way to rapidly generate insights to call the pathogenic variants in the tertiary analysis. So the typical turnaround time is still 2 to 6 weeks in most labs, including our center. Yeah, for the analysis, the secondary analysis take only hours for a patient, but the tertiary analysis, the interpreting and the reporting part could take weeks in most labs. So basically now, if we assume we are doing the whole genome sequencing at a 50-fold coverage depth, then the NovaSeq plus from Illumina can generate the data for 150 genomes a day. But secondary analysis is still slower. If you are running the even with 4 GPUs, L4 GPUs, you still need 130 million, that's over 2 hours to call. If you go to the high-end H100, you still take almost 1 hour. So the secondary analysis is much slower, but even slower is the tertiary analysis that usually take at least 1 to 2 weeks to run the variant annotation, interpretation, and review by the clinical director to get to decide if this case they found a causative mutation in the variant. So the lag is really the sequence data interpreting part. So we developed the AR for metal or AR for rare disease interpreter, which is the AR-based framework for the tertiary analysis in clinical sequencing. This framework can work for the whole genome sequencing data, whole exome sequencing data, gene panels, and we are using AR trying to emulate the clinical geneticists, the reasoning process in variant prioritization and interpretation. The whole system framework is mostly automated, so it can rapidly prioritize the disease-causing variant from the 4 or 5 million variants called per case, per patient. This framework, I work on mitochondrial disease, so it's tuned for mitochondrial disease, but it's readily applicable to other rare diseases as long as they are genetic diseases. So the core engine, you have the LM model, large language model, which I started with Google's Gemini 2.5 in last August, and later I gradually ported them to the open source Queen version 3 local model. And the thing is supported by large knowledge base, including those knowledge base from the large language model, from our own diagnosis report in the past, and also from the MyCKD as another mitochondrial disease database we have been running for over 10 years. And finally, to generate the structured clinical report, that it will prioritize the ACMG classification for the pathogenic variants which are causing the disease based on the ACMG's inference and the guidelines, and also have other diagnosis information about how the genotype are linked to the phenotype and to the disease diagnosis, and also give details of the rationale during this reasoning to come up with this conclusion. And also the report will have some disease diagnosis, differential diagnosis, and some treatment and disease management recommendations. Yeah, this diagram shows the architecture of this system, meaning 2-1. Basically, you have the input from the sequencing, you have input from the EHR, the patient's clinical health record, and also you have knowledge base from ClinVar, HGMD, and other annotations. Then we run the bioinformatics pipeline as usual to annotate each of the variants and filter down the variants throughout those unlikely to be functionally important. Then we go to feed them to the generative AR code, which includes the prompt engineering layer that will take the data from the input, take the knowledge base which are relevant, also take the API calls to the large language model server, then run the Gemini and other large language model to generate the diagnosis report. So basically, this is architecture, and this one shows the workflow, which basically the same information in the architecture. It's only that if you have negative case, you may go back to re-annotate your data and try to run this AI-powered analysis framework again. This AI-based framework was derived from our previous work we call the PCVC machine learning workflow, where we are trying to do phenotype-centric variant classification using machine learning algorithm using similar data. Yeah, you see the middle is about the data from the patient from NGS lab, or from the clinical record. In step 1, they will went through the annotation and variant filter down in the step 2. Then we do deep annotation, variant annotation with all kinds of well-known annotation engines like VEP and like HGMD, ClinVar, and population allele frequencies, and more from you can plug into the knowledge base. And then at step 4, we get the short list variant with deep annotation from all the sources. From here, in the past, you will go to step 5 to run the machine learning model to find the top candidate for the pathogenic variant, and then send to the clinical directors to review and decide if they found this call is the causative variant. But at step 4, now we use the input file also generate a AR prompt for the framework. This is something we implemented starting last August. So this one is about using the same data as the machine learning module now, and you run the prompt, run the large language models to generate different type of clinical diagnosis report. So this system was tuned for rare disease, rare mitochondrial disease. This one I'm trying to show quite a complete case report for the A108124, which this report was generated for serving the clinicians to help them in interpreting by providing traceable evidence and the reasoning process. So first, you have patient summary with the clinical data. Then the second with the HPO ontology encoding, which are essential to link to the disease profiling and the genotypes. And the part 2 is the primary genetic finding about which genes variant was found to be most relevant for these patients' symptoms, and then give very detail, including the gene names, the exact changes, the effect on the proteins of for this gene, and also because this is mitochondrial, it has something special called homoplasmy, which only found in mitochondrial DNA's mutations. And then we have the clean water notation and HGMD, which are the most referenced known causative variant, the database. For this variant, we have report from clean water where it was reported pathogenic, but HGMD doesn't cover the mitochondrial DNA variants, so it's negative for HGMD database. Then the part 3 is actually the most important part for the AR generative report is the variant pathogenicity. So the first it said okay, the classification is pathogenic, and the evidence is that clean-water causes the pathogenic by other labs, multiple labs already cause the pathogenic. Although HGMD and GenB are not so positive. And the second part gets the detailed evidence code for ACMG evidence code based on the ACMG's guidelines, which are the official guidelines for the molecular diagnosis data interpretation. For this variant in the mitochondrial DNA, you have the evidence called PS3, PS4, which are strong evidence based on the data you provided, also based on the data the large language model are pulling from its own knowledge base, pulling from the vector database we provided back context, and also some web search at real time. And this is based on the different type of changes effect of this variant. PS3, because we have new functional studies in model system to provide that these variants are causing functional change which are disruptive for the function of the protein. The PS4 is that it is already reported in multiple times in different patients, so that gets same disease, same phenotype. Then you have the moderate support evidence based on it's not seen in healthy population, you get P-2. If you have another variant, slightly different same position with different change of T2G rather than T2C, but at the same position, so this give you a PM5 supporting. And then are the more weaker thing are the PV4 is weaker because it's known that this gene was associated with this Leigh syndrome and with the phenotype. Then it will summarize this evidence in the 3.3 section, say, okay, this supports the pathogenic classification. And this shows the older version before we put in the mitochondrial DNA variant specific rules in the variant scoring. You see that it gets fewer evidence code pooled. You don't have PS4 and PP4 that we have seen in the last slide. Also, it called something PM1 is not so specific as PM5, because PM1 means that this array, this domain is important. But PM5 says, okay, you have an exact position, a slightly different change at the same position, so it's more specific than you don't have the ACMG guideline tuned for mitochondrial disease, mitochondrial DNA variant. So that means that the better you define the rules to the large language model, the better it can utilize the data and reasoning to give you the evidence code to support the classification. Here is give the disease name diagnosis, also the other less likely secondary diagnosis, and put the literature relevant, put the abstract from the literature based on the data. This supporting evidence for the diagnosis. And here is the last section will give you some therapeutic suggestions, disease management suggestions, which are for information, but it's not clinical advice for the disclaimer language. So basically, we have the detailed introduction about this framework. Here we benchmark the performance. First, we benchmark by creating a simulated cohort with 68 cases. We use the published cases from G4GH. We spark the positive causative variant into a negative VCF file, which are what we generated from the sequencing and filter down in the secondary analysis. And then we run this framework, the AR framework. It get 64 of them correct. This translates 94% sensitivity. And for diagnosis of disease names, we get 49 correct, which are 72% accurate. Actually, this is a high accuracy because in our lab in the past, we usually don't give the disease name because it's hard to get a right disease name based on the patient's clinical phenotype variant. So basically, this means that we have high sensitivity and we also get the disease name quite correct. And each case take less than 5 minutes to complete, actually. So it's quite fast. We also compare with the machine learning-based PCVC classifier. That classifier gets 84% sensitivity, and about half of them are true positives. So it's doing better than machine learning alone, which are not powered by the reasoning from large language model. And we also compare with some commercial solutions, third-party solutions, which we checked the benchmarking last year they released. So those commercial solutions last year, at least, they are retaining you a list of candidates rather than a single pathogenic variant call. And they usually give 90% in the top 2 peaks, and or 94% in the AR Marvel, but 74% only in Diag AR, which are if you limit to the top 1. They didn't give specificity, but because they usually pick at least 2 of them, then at most 1 of them are correct. You have less than 50% true positive or specificity. Here the table we summarized last year based on the commercial solutions of different companies. The first one, which was bought by the GDS for $50 million. They give something 90% in top 2 sensitivity. The second one is more half of the academic one, so they give 66% in top 1 and 94% in top 2. So that at least for the top 1 peak, this 66% is less than what we are getting, 94%. And dark AR is from another company. It gave something slower, 74% in top 1. So basically, yeah, our machine learning PCVC do something similar to them, but our AR-based framework, AR for metal, will get much higher sensitivity as we test it. So basically, yeah, in summary, this AR-based framework is effective for prioritizing the multivariance for genetic testing. The sensitivity is high with 94%, at least for the simulated cases. And this provides a traceable, very structured and comprehensive reporting, which are good for the clinical directors to check the evidence to decide if this call is correct. And the report is human readable than the machine learning results. It gives very detailed all kinds of evidence with rationale and with evidence in the report. And we are running it, importing it to the open source large language model. And it's showing that the performance is also not so good as Gemini, but it's comparable by tuning the prompt. So my next section is about data transformation in clinical data processing. We are trying to use AR to transform the unstructured clinical data, free text, note into standardized ontologies and dictionaries to enable the cross comparison. The ultimate goal is we want to get value from unstructured data, either from the internal record in the hospital or from the publications. For the direct objective, I was asked by a journal to write a paper, so I was trying to initiate something meta-analysis to quickly go through, to create a virtual registry, and use the AR-based acceleration. And we try to set up a framework for transforming the clinical note into standard dictionaries reliably and with high accuracy. For that special topic, I was trying to study the Leigh syndrome, which is a very rare disease. You will see in 1 in 34,000 births only. So it's rare, and usually each publication, each paper give you very small cohort, a few to thousands of cases only. You need to merge many publications to generate a large cohort, so that you can have a well-powered large cohort to do meta-analysis. And also the data, every people also are reporting the data differently, so you need a lot of effort if you manually curate the data to unify the data. For example, yeah, for the collections, 1,600 cases, the age at onset came from 21 different terms, the different table column by the author, the different columns. If we go to the phenotype coding, that is more heterogeneous. For one single phenotype, the decreased activity of mitochondrial complex 1, the author used 24 different terms that we need to recognize, and not only the headers, the 29 terms, we also need to convert the original coding of the values to a standard term to this decreased activity of complex 1. So we devise the AR-powered harmonization pipeline, which it's a hybrid pipeline combines the generative AI reasoning with human in the loop review to ensure the quality. But this is rapid, and we can process the over 2,300 published cases from 46 papers. It's only under 2 weeks by myself in 2 weeks. And the accuracy is high. We get over 90% of phenotype accuracy after manual checking and some refinement of the AI generated mapping. So basically, in 2 ways, I generate a cohort with harmonized data with 1,600 cases, and they are deeply annotated. Each one I get over 6 phenotypes called in these cases to get a rich characterization of the phenotype. So this diagram shows the rough workflow from here. We do the literature search at PubMed with the keyword, and then manually pull the tables, the case level tables from the papers and load to our database, our website. Then we get the data in the SQL database, which are heterogeneous, which are inconsistent between different papers. Then in the step 2, we use the AI-based framework to do transformation. First, we started with Gemini 2.5 in August, which was the best at that time. Then we divided 2 prompts for the data transformation. The first one focused on age-related information. The prompt AI method for age, and the second one is more comprehensive data transformation for all kinds of phenotypes, heterogeneity, mode inheritance, also the genotypes information. These are the 2 prompts we divide. And then we generate a harmonized report from the AI transformation. We load to the SQL database to our website again, which are much more structured and standardized. Then step 3, we use the phenotype human in the loop quality checking refinement using some tools we used in the past for the phenotype mapping for free test to the human phenotype ontology mapping in the past, which was semantic similarity based. But this time we use it to do the QC and refinement. And finally we get the final virtual cohort in the database with over 1,600 cases with 11,000 entries that average 6.5 phenotype for each case, which is a good amount of phenotype for the cases. Then we do meta-analysis, survival analysis, stratification analysis by intersecting with the genes, with the inheritance, with the sex information. Here I just show you we originally select Gemini 2.5 because we compared with ChatGPT 4.0 we compared with open source large language models, but they cannot handle the complex phenotype data we saw in the publications. So we picked the Gemini to start with. This is one prompt for the age processing. Yeah, basically you say, okay, the rules, we define the rules to be simulating the clinical geneticists trying to transform the data. We give some general guidelines to request that to be strict on the data fidelity, avoid any speculations. Basically, we want to avoid hallucination as much as possible. Then the input data format we specify, we generate from the SQL, the columns we defined, and we let the AI know the data columns. And then the output format we specify to the AI. After that, we have the execution workflow we should have listed each step that we want the AI to do based on the data we provided, based on the rules we provided, including HPO term mapping, including the mitochondrial disease diagnosis criteria based on phenotype, based on the different type of phenotype, how important are these required or something optional symptom to diagnose, to make a diagnosis. So the stage 1, we process the raw case collected from the 46 people, 2,300 cases. This will process, the processing take 1 week at Germany because I run it batch by batch at the studio, AI studio, which is manually. Then we do the human in the loop review, which are manual, and also including thematic similarity search, which take another week. So after 1 week, I process them to get 14,000 HPO based entries, and also I threw out some cases that was not very raw data in the original paper. Then that left 1,679 cases in the final virtual cohort. During the process, the AI the AI's first run gets 77% of the term accurate in the HPO term name and the HPO IDs. Then we run through the human refinement, in the loop refinement, improve the percentage to 90%. The AI also inferred some data which are not reported by the author, but the paper, the context allows the infer the information by the AI based on the knowledge base. So, for example, zygosity, we have almost 5-fold more code in the AI generated data. So this is the raw data, which are very free text. The right side is the free text, the raw data. The left side is the AI transformer data. So basically, the clinical data, we get some code to the phenotype names. We also get some biochemical lab testing, which are numerical values. We need the AI to convert them to some clinical phenotypes based on the rule, based on foundation models, knowledge about how the lab testing should be translated to, is this normal, or is this decreased, or is this increased, this kind of information. AI can do this quite well during the process. Also, in the original paper, there are lots of abbreviations in the publications that you see the middle. There are dozens of abbreviation keys that you need to expand them to the 4 phenotype names. If you are doing manually, that each cell, many cells, you need to do it manually to expand using this key pair. But with AI, you see now can do this mapping quite accurately. So finally, we have each case, the AI will process the data based on the abbreviation keys you provided, based on the HPO mapping rules you provided in the prompt and other rules, based on its own knowledge, based on the internet search, translated to the middle, the AI standardized the phenotype code from the raw phenotype in the right side. So basically, here shows how the AI was doing the phenotype mapping from the raw clinical node. The majority of them, they can derive from the clinical description, although they are transforming to the standard name used in the dictionary. But there are some, the second is some biochemical lab testing. If you translate them based on the knowledge, general knowledge, the numerical value will convert to abnormality cause, decrease activity, increase activity, or something like that. And also there are something other, not very direct clinical information also can be transformed by the large language model. And for human in the loop validation, quality checking, we see that group A 0.2, this time where the AR gets the mapping correct very accurately in the first run. That's something over 90%. And in group B, there are something almost 10% of them, they get the phenotype terms right, which because the terms are long, they have better match to the clinical node in your raw clinical node. But the HLQ RDs, actually, they are meaningless. It's only a single RD with 6 or 8 digits. So it has a hard time to match them correctly. And so also in group C, we have something, the terms matched are quite far from the standard terms, although thematically they match to the HPO ontology dictionary. That's why we use the thematic similarity search to do the refinement by human the loop in group C. Then finally, we improve the accuracy to over 90% from the AR-based mapping. So basically, after that, we get this and we load to our website, which we have a web resource for the virtual cohort let user to access and search the cases with different clinical phenotype or combination of phenotypes and check the details. So this is the tools we have. And then, after we transform the data to standard terms, now we can do some clinical characterization of the cohort to do meta-analysis, which is 4 times larger than any of previous reported cohort for the Leigh syndrome. We have now a much higher percentage demographic information available, the sex, the age, we also the age of onset. We know that 41% are infantile or earlier, 34% are childhood. So that this disease is quite early onset for the Leigh syndrome. And inheritance, we have most of them are autosomal recessive, and some inherited from the mother, the mitochondrial inherited 752 of them. And after we standardize the phenotypes, and I use the gene ontology tree to consolidate to some more general form. We can identify the hallmark phenotypes which are important for make diagnosis, which let us make diagnosis based on the genomic changes based on the phenotype in the cases. And most of all, interesting is that we now can do some survival analysis, which was not possible with a small cohort in the single paper. Now we merged, we have 709 cases. We can calculate the exact survival time in numerical value of years based on the age of onset, age of death. This gives us sufficient statistical power. So with this, we can see that mitochondrial translation changes are associated with the worst prognosis, because the 84% of them will die, and for this group, if the disease started under 3 months, which is 0.23 years only, very early onset in the lifehood, and they survive very, very short time. And we also found the TRMU gene, if they have the change at the second position of cDNA, then this will have survival time only under 4 months, which is very poor. And then we get this conclusion because we combine these from multiple papers that we can rely on to give this conclusion. And for the mitochondrial complexes 1 through 5, we see the complex 5 have the worst survival, only less than 2 years. If it's affecting the complex 1 or complex 4, fall, then the survival time much longer, but still under 4 years. So this Late syndrome with quite something. Unfortunately, the shorter survival time if they are affected. And we do the survival analysis based on the larger merged cohort with 700 cases have exact survival years, so we can now stratify by the genes, by the age of onset, by the sex, and by the gene function group. So for the sex, we see that the females and males, they have a similar onset to the left side. But after 10 years, the female patients will have better survival rate than the males. After 10 years, we have this conclusion after we get a larger cohort merged. And this one about different genes, the worst gene is the TRMU to the bottom. It's a very early onset, very low survival after 10 years. But if the gene was the mutation was affecting another gene, ECHS1 or ATP6, then survival time are much better. Even after 10 years, you still have over 60% survival. Yeah, from this work, yeah, we have publications from this work. The first one is the Late syndrome cohort that we published the early last month, which we processed 2,500 cases actually, with 126,000 data points. We transformed with AI, with Gemini, and we published this. And later on, we expanded this AI transformation, and now we ported the program of the AI framework to open source with the Queen version 3 with a local 30 billion parameter model that we run on laptop that we to transform the data, which we also get a very good transformation with age information, phenotype information, the inheritance modes, and also the genes and mutations using the open source large language model now. So that we have systems that are not only powerful, also low cost to use. Yeah, this in comparison, yeah, 2 months ago, there's another paper by a German lab that they do something similar for building the virtual cohort for mitochondrial disease. That paper, yeah, they published the first paper 4 years ago. Then in the 4 years, they added another 3,900 cases to the virtual cohort in 4 years, and they have over 10 people work on that. So because they use the manual work, so you see that it's quite time consuming to do the transformation for virtual cohort in mitochondrial disease if you are not doing it with AI or something computing tool to use. Yeah, actually, yeah, we do the transformation of 11,000. It's something I started in mid-December using the open source-based language model. Basically, I did all the transformation and human the loop validation by myself. You know, and 1 month, also, yeah, it's over 10,000 cases with AI. But from the data, yeah, I can reliably, yeah, see, I can write a paper. The second one, we already completed the writing based on the data. So the AI is very powerful, very fast to do the data transformation. Yeah, also, yeah, so basically for the data transformation, yeah, we have the word-to-term framework using generative AI, get a quite satisfactory performance that I can trust based on my experience and my knowledge in curating the clinical data. And for the Late syndrome, we already generate the largest virtual cohort, over almost 2,000 cases. This is 4 times the largest than anything in the past. And the mitochondrial the disease cohort is also larger than the German group generated and published at a decent journal. And this framework can work on any rare disease from literature to do the data mining. So we have this, so the prompt was attached in the supplemental of the first publication. Also, going forward, after I completed the two papers writing, going forward to refine, so reduce the manual effort by reduce effort in the human in the loop part, further to improve on the pipeline. This is the one you see that we have a free text clinical node, something non-standard, something even spelling errors in the raw clinical node. Then we run the AR for HPO annotator to do the transformation. Then if you're in the first run, if you run the phenotype based on the understanding, based on your HPO definitions you provided, and also from your prompt, or also from the backend vector database, then it will get the first pass. This will transform the raw free text to the raw phenotype snippets, and also infer to the standard HPO ontology term and RDs. The terms by review is quite correct, but the RDs are mostly wrong, so that we provide as we see in the past pipeline. So what I did is I get the human in the loop part, the semantic similarity search I used manually in the past. I run it in the backend, prepare input for each term. I pick the 20 best match based on similarity search, semantic similarity search, and then I run the AR second time to review the up to 20 candidates for each raw phenotype, up to 20 top candidate phenotype HPO term. Now I have the semantic search get the HPO RD is very exact correct. I only need the AR to pick the right term with the right HPO RD. So now we have the best pick by the AI, which almost all the phenotype RDs are correct now. Although they are meaningless, they are only RDs, but now they are correct. Of course, the phenotypes in the HPO terms are now very correct. So I have system now. This is something you see. The first step takes something 36 seconds with the local open source large language model running a task on my laptop. And the second round runs something still under 41 seconds. That's the thing. It takes less than 2 minutes to do a batch of input up to 10 or to even 20 clinical terms and map them quite correctly without you doing anything. You just wait 2 minutes to see the results, and if you have table generated, you can save the table to CSV something to do it. So basically that's it. So together, I think now the large language model and open source tools, open source spirit, we have open source large language model, we have open source tools, bioinformatics tools, or other tools in the past. We can combine them to democratize the data science part for precision medicine data processing. We no longer said, okay, we need to rely on the commercial companies, solution provider, which they run those hardware, large database, $1 million to set up, large team to maintain it. But if we only want to get some quick answer, we may do it locally without data going out, without privacy worrying. You can run something hardware at yourself. For myself, this everything together under $5,000. The most expensive is a Lenovo laptop, 24 CPU with 5080 GPU. These are moderate with only $3,000 for my to set up those things to run this as web server, website at my home. And I won't need to get data out to them to get the agreement of data transfer, those kind of things. Yeah, supposedly we can get similar infrastructure to the clinical production, to the hospital, to get something set up similarly without very expensive hardware, but you get some satisfactory performance. Of course, you can always get better performance, larger language model, larger model, higher end hardware, but it's not absolutely essential if you can get the rules, get the data input correct. I think that's the thing about my talk. Yeah, this is about timeline. In August, I started to do this work because the journal asked me to write something without paying publication fee to them. So that I rushed to generate this pipeline to do the data preparation and generate the pipeline. I first started with the Gemini with the paid solution, then I tried to port to open source solution, first to the Kimi, which did well in December, but I didn't do much because it's still paid service. And later, when I got on the new computer with good GPU, I started porting to local large language model on my computer. So in December, I set up the data transformation part, and in January, I get the genetic testing data interpretation part work. Running, you see the large language model is quite a small language model actually. That's it. Yeah, finally, yeah, all kind of people in the whole children's hospital and in our team, and also the Collaborator Children's Hospital, the Children's Hospital Philadelphia, and also other people. James, yeah, we worked together for many years. Also, my wife is listening to me here. So also, yeah, you was the talk. That's my talk. Thank you for your attention. Okay.
Are there any questions? And I will come with the mic as soon as I can get it turned on. There you go.
Yes, thank you so much.
Sure.
So Li Shuang, even though right now you have a trained retrieved augmented generation with Qwen 3, have you thought about creating your own micro LLM for doing just this work?
I have it on my computer. I have it in web interface on my computer. I have web interface call to do the transformation at the website, the regular website. For the molecular diagnosis report, I need the data preparation, different annotation, as I show in some slides, the PCVC part, that will need to run offline. But we have the thing in the part at our hospital that I set up to run. Yeah, but it's running as calling to the large language model. It has an API interface if you open it with a key. I'm not going to agentic work yet because for now I wrote a very long prompt, over 3,000 words, to put the things in, all things in my mind. I think they worked well, so I'm not trying to go to the agentic programming yet.
Sure. Well, maybe that would be something if you think about if you want like an idea for a research grant to take that on. But yes, but this is great work.
Yeah, I'm trying to see, okay, because we have been doing processing all this data, which are very tedious. Even no matter supporting the clinical director in our hospital, no matter the mitochondrial database that I was trying to make to the public, open, like I said, to the world, it takes a lot of time, took something passion to do those kind of work. It drove you crazy to map the data but manually. But now you have something that can do the work for you.
Hey, I saw on one of the last slides Chiwen 30 billion parameter model.
Hmm?
I saw that when you were doing porting on open source models.
Yeah.
I think you mentioned that you were using Chiwen 3 with 30 billion parameters.
Yeah, that's the model I ran actually. Only the 30 billion model as quantized to the middle Q4 is not high density. It works well. It surprisingly works well. Actually, I ran the new 3.5. It's much slower, but it's not much more better because I think because I ran it many times, it have the history, have something to the context in this instance running on my computer.
Did you test other models? Was there other models that were not working for you, or?
Actually, I ran the open source from OpenAI. They released something that's not doing well. I also ran the Granite new model. It's not doing well. The main thing is that they are not generating report in the format I specified that I show here. I want it in the consistent format as I got from Gemini, as I got from Queen. But those models, they can do something good maybe, but they are not generating report in the format I wish I see.
Well, thank you very much for the presentation, everybody.
Thank you for my talk. Thank you. Okay, thank you.
You seem to have you want to do it. That's fine. All right. We'll turn this off. All right. However it turns off.
Thank you. So now I'm at UCLA, but yes, this was really great. I first introduced a lot of natural language processing to SCaLE, and this model was one of those that started using natural language processing, and then of course the next cutting edge part of that was large language models. Oh yeah. I felt tech had started with natural language processing, and of course that now of course that all of that cutting edge research lies with large language models. We do far more natural language processing with large language models. Yes. But it's good to see where they come from. It's also
How do you turn this on and off? He just brought.
What's wrong with it?
No, nothing's wrong with it. I just don't know how to turn it on and off.
I'm assuming you want the.
Do you want microphones or this ear thing? This?
I like microphones better.
Good, excellent. Then we don't have to worry. And you're the last presentation, so we don't have to worry. Good. Here you go. Hello, hello, hello.
David, go out into the hall and bring people into our talk.
Yeah, y'all satellites are here.
Yeah. Open source and space. Oh, I want to hide this down here. Will you promise me not to kick this while you're on this?
So I think I think that this is what medicine really needs. I think it's
The clicker doesn't work anymore. It's probably fine.
much easier for
So these are stickers. You can hand them out to people who ask questions.
Excellent. I can do that.
Yeah.
They get it. All right. Very nice.
You can give one of the stickers to me.
Right away? Right away.
and cases where
We're gonna hide this too.
missed by
Are you ready for this?
Yes. Probably.
be picked up by a large.
There's enough room in this yellow box.
I'm going to take this and put it away. Put this here, away. This is for me, this is for her. This is for me to give away.
But yes, I'm glad to, that we have these technologies.
It went away. Joys of modern medicine.
Academic exercises, but real academic, clinical use.
Well, I had medication too, so.
Oh, come on, you have done a lot.
They're opening the doors to usher people out. They gotta walk the house. Yeah, we gotta pack the house here. Although, the last time I did a talk, I think it was in this room, I had like 20 people maybe, and so it was kind of a disappointing audience in size, but they asked questions for 2 hours after the talk.
That's
To the
very
point where
long.
the AV team that I work on shut down the feeds and walked away. It's like, really? So,
They do that same thing. They said, you're done. So
yeah.
pull the wires.
There we go.
How long is the talk?
It's an hour.
Hour.
Yeah, sorry, Sam.
But we're the last talk of the day,
Could you-
so the only people there to stop me are Ron
you
here
just
and
test this?
Proctor Smith upstairs.
Testing 1 2 3. Testing 1 2 3. Hello. I am holding my microphone like I'm singing. Okay.
There you go.
Just close enough.
Oh, this is a strain on my arms. No.
Then I have little cards, like 10 minutes, 5 minutes, 1 minute, to warn you. Oh, she's not listening. Oh, that's okay. I have little cards, 10 minutes to go, 5 minutes to go, if it goes that long, but it probably won't. And then at the end, you can say questions, and I take this around and wait till they have a microphone, because we're recording the wonderful questions. Okay, done. All right.
Mic test, mic test. That sound okay?
Excellent.
You sound good, I sound good.
I sound excellent.
Yeah, it's a co-presentation. Yes.
That's
Yeah.
why we're both. Yeah, I'm taking.
Yeah,
13
Inez got
spots.
the headlining spot.
Is it really 1 hour? Yes. Okay.
You don't have to stay for the whole thing.
Because I parked outside like 2 hours, so I need to move the car.
Oh, you should go move the car. You've already seen this. So.
You've not seen this?
Yeah, Sam saw it in Tokyo.
No.
This is the 1 hour version of.
This is the extended version with all the nitty-gritty details and cool anecdotes and all sorts of wonderful things.
And we also explain what a satellite is, which I'm sure you know already.
All right. Hello, everybody. We're going to go ahead and get started with the talk here just after 5 at the Southern California Linux Expo. My name is Michael Starch. This is Ines Cuider, and we will be talking to you about 5 satellites in 5 months, how we delivered rapid, reliable, and open software. So first, before we jump in, I want to state there's plenty of time for questions in this talk. So if you have questions, we want to hear them. We have some incentives for people to ask questions that you may or may not see. So I don't know, maybe ask some questions. I'd also like to do a shout out to all the volunteers and staff here at the Southern California Linux Convention. You know that, or maybe you don't know, this event is mostly volunteer run. So shout out to all those volunteers working hard. We've been volunteering for the AV team, which was amazing. And I just did the thing that I was not supposed to do. So anyway, we'll get to that in a second. So what is our agenda today? We're first going to talk to you a little bit about the introduction to the Proofs software. We're going to talk about what are CubeSats, who are the Proofs 5, and what is CubeSat software. Then we're going to talk about the development strategies we used to develop this software. So we're going to talk a little bit about what MVPs mean in this environment. We're going to talk about how we leverage the tools available to do development. We're going to talk about testing, because everybody's favorite topic is testing. And then we're going to talk about how we streamline decisions. We'll close the talk today with a bunch of lessons learned, where we'll talk about the plan for changes, practical concessions we had to make, everybody's favorite, beware of state, and how we learned to trust the team. So I wanted to talk a little bit about who we are before we jump off this page. Again, I am Michael Starch, and
I'm Ines.
we are from the Open Source Space Foundation. So we're talking a lot about the Proofs project today, but that project, the hardware plans and the software that we've developed is released to the public as part of the Open Source Space Foundation. So everything we talk about here today, you can go find online and have fun with, and possibly even launch to space. So let's go into the introduction. The first question is, what is a CubeSat? This is a CubeSat! And a CubeSat that I probably just damaged by kicking it down to the floor. Sorry. Yeah, hopefully. Free vibe testing. There we go. We did it. All right. So for those of you who aren't aware what a CubeSat is, it's a spacecraft, which is really cool. So this talk is about spacecraft running open source software. These CubeSats have everything that you expect in a normal spacecraft. They have attitude determination, they have communications, they have control software, they have payloads, and they have smiley faces on the back. So these CubeSats are really full functioning spacecraft. The thing that makes a CubeSat novel is its size. So you can see I can hold this CubeSat in one hand, and this is actually twice the size of the smallest CubeSat that most people talk about. This is what's known as a 2U. And you can see on our picture here, we have some 1Us and a nice little CubeSat plushie to round out the mix. CubeSats are small. They make it easy for institutions like universities and other groups to launch small, high-risk payloads into space so that we can study and test things in space without the traditional multi-million-dollar cost of a satellite. So who are the Proofs 5? The Proofs 5 are 5 universities that conspired, if you will, to build this particular CubeSat. So we have the SlugSat team from University of California in Santa Cruz. We have Cal Poly Pomona Bronco Space. We have the Texas State Space Laboratory. We have the Columbia Space Flight Initiative, and we have Northeastern. So these are the universities that work together to build this open software and open hardware to build this kit that we can put into space. So our project is about how we built software orchestrating 5 separate universities in 3 separate time zones, and did it all fairly rapidly. So to take another look at the team, this is our team. Our team is composed of a number of people that you can see here. These are pictures from integration and delivery of the satellites. And our team spans all of these universities, but we came together to build this spacecraft. So I'm going to hand it off to Ines to talk a little bit about the project in more of the numbers, and then we will get into spacecraft software.
Yeah, so the Proofs project started a little less than 2 years ago when we got a grant from CSLI, the CubeSat Launch Initiative, to launch 5 satellites. Since then, we spent about $35,000 USD, which is very, very cheap for 5 flight unit satellites. We soldered 540 solar cells, 95 flight controller boards, and a lot of iterations. So we started with the V5B, and then V5C, and then V5D, and then V5D Prod, and then V5D Prod Rev 1, and now we're on V5D Prod Rev 2, right here. It's fun to see all of our circuit boards because they're like green, and then we had like an era where we had black ones, but then we were getting so close to the deadline and the green ones come like a week faster, and we really needed that, so they went back to being green. We also crimped space grade wires, so we crimped about 700 wires. I can't hear the sound of the crimp tool anymore without like looking around me for the evil crimp man. We made 9 engineering models and 5 flight models across all 5 universities, which you can see there. Those are the flight models. Gonna go quickly over kind of the missions of each of these satellites. So over here on the far, what's this direction? On the far right, we have the UC Santa Cruz satellite. Shout out to UC Santa Cruz. UC Santa Cruz's first satellite, their payload is a ballast payload to look at the orbital lifetime of the satellite in orbit. Then we have Columbia University. Their payload is like a little deployable door, and a little lion will come out. So it's like a selfie stick. It takes a selfie of a little lion in space. Over in the middle, we have Cal Poly Pomona. Shout out to Cal Poly Pomona over there. They have the 2U, and so because they have 2Us, they decided to go with 2 payloads. There is a radiation sensor payload as well as an S-band radio payload, which is actually very fun because the S-band radio payload was developed by SatNox, which is another open source project that we're helping test, and that's in collaboration with the University of Hawaii. And so as we're doing payloads, we're also contributing with other universities and other open source projects, which is cool. Then we've got the Northeastern satellite. They also have a camera. And then the Texas satellite, they also have a camera. And they've also got an open source payload called Mosaic, which I would highly recommend looking into later. They do, like, for university teams, for students being able to swap out sensors in kind of a space grade way. And so they're also doing a radiation sensor payload, but as part of an open source platform. And so it's really, really cool that we're all working on these together. But it's also like we're doing 5 satellites, developing 1 software stack, and all of these different payloads. And we got to do it all together. Talking a little bit more in general about what a CubeSat software looks like. Here's a picture of a ground station that one of our team members from UC Santa Cruz is working on. And a picture of our satellite, which not to scale, how it will be when it's orbiting. What the satellite has to do while it's orbiting the Earth is it gets signals from a ground station, it gets commands, and it also downlinks telemetry and events and all of this data from the satellite. Some other software that the satellite has to do is has to detumble a spinning satellite after deployment. And so often, the ISS doesn't do this anymore, but they used to like throw the satellites out like a football. Now they have like a deployment mechanism and like a robot arm. And then if you're on a rocket, there'll be a deployment mechanism too. Often the satellites will be spinning after that. And so you want to orient yourself based on like the Earth's magnetic field using what we call a magnetometer. There's also light sensors to know where the sun is. Some satellites have cameras called star trackers, which track where they are based on the sun. We didn't have that. It was too much development time. But we also didn't need it for the type of detumbling we were doing. And the reason you want to detumble a satellite is to communicate with the ground station. If you're spinning really, really fast, it's really hard to get a radio link to the ground station that is really good. And also if you're taking pictures, like many of our satellites had a camera, not a really good quality picture if you're spinning really, really fast in space. So we have a detumble mechanism. We also manage operational modes. Crazy thing about satellites is you can't turn them on and off again when they stop working in space. And so you have to make sure that you think of all the operational modes, all the things that can go wrong, and that it can solve any issues that come up for itself. And part of that is having a safe mode, where if something non-nominal happens, or if the power goes below a certain level, we go into like a power saving mode. Actually, Sam over here in the second row, he was a big part of our mode management system. We also have integration with ground station commanding, so all of that bits about event and telemetry that I was talking about. And then enforced ground user authentication. This was especially important with our satellite. If anyone here is a radio amateur, part of our payload is actually that any radio amateur, if you've got like an amateur license, you can ping our satellites, and you can ask our satellites for a joke. And they will downlink the funniest joke you've ever heard, I promise. So if you don't have a radio amateur license, maybe consider getting one. We're launching in April, deploying in May, and then you can get some jokes. But because we're telling people to ping our satellites, we don't want people to ping our satellites and start telling our satellites to do things that may be bad. And so for that reason, we have like security and authentication on our satellites. And if there's any questions later about the stuff on our software, we're more than happy to talk more detail. But we're more talking about the development of the satellites. This is just a thing. Okay, so now we're going to talk about our software development. And why did we develop software in 5 months for 5 satellites? So the Proofs Kit is a long-running open source project. Cal Poly Pomona has been developing it for a long time, and they've launched many satellites with it. But as we were developing this project with all of these universities, we were using some legacy code in this program called CircuitPython. And CircuitPython is great for students because Python is kind of easy to learn and pick up. But what we were realizing is CircuitPython was a very long legacy code. And because of that, it was getting harder for people to pick up. It was also getting harder to collaborate because the architecture of CircuitPython was not very conducive for building embedded systems, especially complicated embedded systems like satellites. And so it felt like we were refactoring things kind of over and over as we were trying to add new features. It felt like 2 steps forward and 1 step back. And the other thing with CircuitPython is it had a lot of limitations. For example, it had limitations with you can only have 1 thread, which is a little bit rough when you're doing a lot of flight critical things on satellite. And so with 5 months until handoff, we decided to switch to F Prime, which is an open source componentized flight software framework developed by JPL, and Zephyr, the real-time operating system. Also open source, developed by the Linux Foundation. And this has a lot of things that we want in a satellite. F Prime is statically compiled. Zephyr is a real-time operating system. There's all of these safety features within it. Also, from a design point of view, not only does F Prime have flight heritage, flight heritage means it's like flown in space before. That's a very important term in space. If you ever go to like a space guy and they're like, our tool has flight heritage. And so they're really happy about that because they can sell it easier. And so a lot of the tooling that F Prime has, it's a component-based architecture, which means that you're able to kind of split off the individual things you're developing in F Prime into these small things called components. It makes it really easy to test and communicate and debug. And as we found out, it made it really easy to plan out what a satellite architecture looked like. So now we're going to talk a little bit about our lean development. So first, I'm going to talk about our iterative minimum viable product. Over here is our real whiteboard diagram when we decided to restart our flight software from scratch with 5 months left before launch. And we went and we wrote out everything that was on the satellite and all of the software that we thought was important to be on the satellite. Starch is going to point some stuff out from us. At the top, we've got our antenna board. Our antenna board has a distance sensor, a temperature sensor, and a light sensor. It also has the antennas, which we use to communicate. Over in the middle, hidden under the evil face, is the flight controller board. That's the brain of the satellite. On it, we have 2 radios, a UHF radio, which we mainly use, and it's what radio amateurs talk to, and then an S-band radio, which is more useful for us for things like high data rate stuff. We also have an SD card, an I2C MUX, a watchdog timer, a bunch of other fun stuff. Then we've got a battery board, which has a temperature sensor and the batteries and the battery stuff. And then on each of the corners, we've got our XY solar panels. Those are the solar cells that we soldered 540 of on those faces. And they also have temperature light sensors and then motor drivers, which are the drivers that allow our satellites to detumble. At the bottom, that's a hole because we took the payload out, but there's usually an XY panel as well. And over there, there's a bunch of other things, CDH and COM modules, and all of these things that we want for our satellite. And so that's a lot. It's a lot to develop in 5 months. It's a lot to develop safely and robustly. It's a lot to make sure it's all able to run together. And so as a result, we developed an iterative MVP. What is the minimum thing that can be on the satellite that we would consider a mission success? And we would do that, and we would also every week revise our MVP. And we would see if it was still what we thought was the most important. The big thing when you're doing space systems is risk. You have to understand what you are risking based on the decisions you're making, because what flight software really does is risk mitigation. And what F Prime and Zephyr really did for us was also risk mitigation. And so an example of us kind of pivoting from an iterative MVP is we have a distance sensor on the antenna deployer. And we wanted to use that to make sure that our antennas had deployed successfully. That's important because then we know we can communicate with the satellite pretty reliably. But then when we went to work on the distance sensor, we realized that there was no Zephyr-supported drivers. And the amount of time that it would have taken to get somebody to completely rewrite that was not within like the 5-month framework with everything else that we had to do. So we said, okay, what is the risk of removing the distance sensor from the satellite? And what we found was we found 2 risk mitigation strategies. First, we decided to have a deployment process that tried to deploy 3 times. And so even if it didn't know whether or not it would deploy, it would try again. How we deploy actually is kind of fun. There's a resistor at the very top here, and the resistor has a little string attached to it. When we turn the burn wire on, the resistor gets really, really hot, and it melts the wire, and then the antennas go like that. And so if we just turn the burn wire on like 3 times for an amount of time that we've properly tested, that lowers our risk a considerable amount. The other thing that we talked about is there is a way operationally to save the satellite if it doesn't deploy the antennas properly. And that is get a really, really big antenna dish and just yell really, really loud. And even if the antennas aren't deployed, then it can still hear the deploy, deploy, deploy command. And we had like a university we were friends with who had an antenna that we would potentially borrow. And so we were like, all right, we have 2 risk mitigation strategies. We know we don't have a lot of time. We're going to table this, and we're going to iterate on our MVP. And that's what we would do every week. So that was a pretty cool lean development thing that we did. We also did leveraged development. What this means is we leveraged the frameworks that we used. So the first framework that we used, F Prime, really awesome framework. It's componentized, like I mentioned. So over here, we've got like a component diagram. We have the payload communication component, and then the camera handler component. And those used to be one component, and they used to just handle the camera. And what we said was we have 5 different payloads, and several of them are using UART. And we want to be able to test the UART stuff. And like we've also got a multitude of different codes. And so what we did is we separated all of the UART communication and the handshake protocol into a component that was easy to test. And we told each university to develop their own camera handler. That was a very small, lightweight component that even if somebody didn't have a lot of software development experience, they could still like look at what the camera handler looked like and develop something that looked pretty similar and that would work. And that allowed us to have leverage testing. It also allowed us to have the 5 satellites look as similar as possible. It was also really cool because F Prime comes with a Zephyr UART driver, which has been tested and validated. Well, not necessarily on flight, but we didn't have to develop all of these other components ourselves either. We leverage Zephyr as well. Zephyr has drivers for stuff that already exists within Zephyr. And the really cool thing about that is that we do hardware and software code collaboration. And so when something didn't have great support on Zephyr, our hardware guy would come and he'd be like, I got you. This temperature sensor exists on Zephyr. We can put that on our next version of the flight controller boards. And I mean, you guys heard we had a lot of versions. And so we were able to iterate concurrently on hardware and software. It wasn't like, hardware is done. Now this is a software problem. It really was a collaborative process. And that made it really easy for us to iterate quickly. Another example is that when we were writing our software, we realized that the radio couldn't reboot properly after it had gone below a certain voltage. And so talking to the hardware team, they were able to add a proper reboot pin, which was a problem discovered in software. And instead of adding a lot of like additional problems to software, there was just a quick hardware fix done for the next iteration. And also an advantage of developing software quickly, because if we hadn't done all of this mode management stuff very early on, we might have not caught it right away, and it might have been harder to iterate on the hardware. All right.
So now we're going to talk about everybody's favorite thing, testing. As you've already heard, we had a strong collaboration between our software teams and our hardware teams. This is kind of abnormal in industry. Usually you get the hardware and then the software people have to fix all of the problems. And, well, my friend who works in aerospace software has many fine things to say about that. But in the end, what it comes down to is software fixes the problems in hardware because software is easier to spin than new boards. But when you iterate, you can actually reduce the overall time. But it means you need to do realistic testing. If you're not testing on hardware and you're working in the embedded environment, you're probably not really testing. So you can run all the tests you want on your laptop that do the unit tests and prove the code and everything looks good, and then you jump on the hardware and realize, oh, I'm out of space. Oh, I tried to use a pin that didn't exist, and the whole thing goes up in smoke. Hopefully not literally. And so as a result, on this project, we deployed hardware-in-the-loop testing as part of our continuous integration process. On every pull request that we did, every change set that came in as part of our software, we deployed that onto our hardware, onto the realistic board, sometimes this exact box, to make sure that we could test on the actual hardware that was going to space. That shows us that our software runs well in the realistic environment. If you don't do this, you start to run into problems with, are there enough resources on this board? Are the assembly pieces of the hardware done correctly? Are you missing things like a wire to reset the radio? And so that kind of realistic testing is imperative to make sure that your hardware-software co-developed solution works correctly. The other thing that we did was realistic in situ testing, or at least the best we could. It's kind of expensive to send Ines here up into space with a multimeter to look at the CubeSat operating in space and test it to know if we can launch it appropriately. That would be a very expensive testing campaign. However, what we can do is climb to the top of the mountain that is over there, Mount Wilson, and we can also send a team down to Signal Hill in Long Beach, and that gives us a line of sight pretty much unobstructed of about 50 miles. So that gets us a realistic test of what this thing might do in orbit with respect to its communication. Because we are transmitting over a 50-mile air gap using these antennas and talking to it. That's that image that you see over there. It's several of us standing on top of Mount Wilson, looking down at Signal Hill, and since it's the future, they were also on Zoom and we were talking to them as they were actively testing with us. Discord, sorry. It's more of the future than I remember. So, as a result, we could do realistic comms testing without leaving pretty much Southern California, which gives us really good confidence that once our antennas are deployed, we're going to be able to talk to them in space. And there was some concern because some of the drivers that we used from Zephyr didn't give us the same gain settings that we expected with the chip. Doing this kind of realistic testing here on Earth builds confidence for when you're going to send this thing into space and not have a reset pin, except the one the hardware team added. The other thing that we did that really helped development was streamlining decisions. We invented what we called the rule of two. The idea behind the rule of two is any two people can make a decision. Should we make a decision here live today? All right, I'm getting the yes. The idea is if two people on the project agree on a decision, let it be so. You should be able to trust your team to bring in the right experts who know the right things to say and discuss. This is in counterposition to what I've seen in aerospace software, where you get every single person in the room and jam them all together and say, let's come to a consensus on a decision. And the first thing that happens is everybody says, well, I'm on vacation. I'm fetching coffee with my friend next week. And so 3 months later, you schedule the meeting. And then you try to bring 90 talented people to consensus. It doesn't work real well. Takes several meetings. So now it's been, 6 months or a year, and you're finally getting your decision. Well, if you have two people sit down and say, who do we have to involve in this conversation? All right, let's make a decision with just those stakeholders and try it. You've tried a solution within, a a week, a day, an afternoon, maybe even 30 minutes. That's a lot faster than 6 months. So rather than striving for the perfection of absolute team consensus, we developed this rule that any two people could make a decision and try it. And as a result, we could iterate much faster. And yeah, the first try might be wrong, but the second try is probably right. And the third try is most definitely right because you're converging on a solution. And so 3 afternoons rather than 3 months. This kind of decision streamlining process took what is traditionally a very long time to make decisions and changes and compressed it into a schedule that we could complete in 5 months.
All right, and now we're going to talk about the lessons that we learned along the way. So the first lesson is to plan for changes. Over here, you guys can see the proofs project flight image, and then you can see the proofs flight configuration hotfixes, and then you can see the final flight config, and then you can see the final cubed flight config, which is kind of nice because it is a CubeSat, so maybe it was always meant to be. And so part of how we mitigated this is that we try to have a final code freeze and then a final bug freeze, where we left a lot of time for bug fixes. But of course, sometimes things would come up that we hadn't realized within this last minute testing. So an example of this kind of hot fixes that we looked at is we had authentication on our satellite. And an important thing about authentication is you don't want somebody to send a bunch of malformed packets to you and spam the satellite, and then you keep getting like the message, oh, this is invalid, 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 invalid. And it drowns out all of your valid packets. That's a valid attacker way. And so what we said was, oh, after the final code freeze, we're going to throttle all of these events. So they're only going to happen 3 times, and then after that, on next boot, they'll happen 3 times. But if you have the wrong authentication and you didn't see those 3 messages, there's other ways for you to see telemetry channels and stuff, but we're not going to prioritize you knowing every single message that is malformatted. And so we went to throttle all the events, and we realized, oh no, there's these 2 events that we can't throttle, and we can't throttle them because they're in upstream F prime. They're not in code that we can directly edit. Now we could fork upstream F prime, and then for the rest of time have to continuously maintain our fork of F prime as related to with F prime. Or what we could do is we could edit this sequence that we have. And we had a startup sequence, which would happen on startup. And that was in charge of deploying our antennas, for example. And if we do that, we can throttle those events specifically on startup, and then we don't have to worry about actually editing the inner code because we're past the code freeze, and we really don't want to edit things that are on the board, especially because we are on a very small memory microcontroller, and our RAM usage was a little worrying. It was fine, but we're not going to play around with the image too much. And because we had planned for we are going to fix bugs, things are going to come up that we don't know. When we do configurations, we'll discover things. We were able to plan for that. But as you can see, we didn't make this is all of our hot fixes immediately. So always know there will always be more hot fixes. Another lesson that we made is practical concessions. So Starch was talking about the rule of 2. Part of the rule of 2 is sometimes 2 people will approve something and it will pass all the tests. But there'll be an edge case that you guys haven't considered. And that's normal because if you're not spending a week thinking of everything, things will walk past you. But what we said was practical concession. We have to just accept that there will be reversions. There will be things that are merged in that aren't perfect. And we'll just accept those, we'll revert them, and we'll work on them on the side, and we'll just keep going full speed ahead with main. And so that was really helpful. For one, it helped us move quicker. Because instead of maybe reviewing something for 3 weeks or talking to a lot of stakeholders, we're able to identify the problem within the code pretty quickly as people were running different things. And then we were able to revert and iterate. So it's okay to not have everything perfect right away. You just have to make sure you identify and remove problems as they come up. Another practical concession we made is that our integration suite of tests that were running on GitHub Actions were being a little bit buggy. And I think part of the thing is you have to see what the difference is between your testing framework and your actual flight software. And so what was happening is we were having issues with the actual testing framework. And so debugging that, especially really close to integration, we didn't deem was the best use of our time because we really had to close out a lot of things. And so what we ended up doing is we mitigated risk by other ways, by like making manual tests, by running manual tests, by running local tests, the same integration tests locally, and by ensuring that we validated everything that we did. But we moved away from those automated tests, which when they make your life better, they really do make your life better. But if they're making your life harder, then you got to pivot and find a way to make your life as good while still mitigating risk.
So the next thing we learned was beware of state. I feel like every time I give a software talk, I'm giving this particular lesson learned, which is state can be dangerous. In this case, we wanted to show a quick demonstration of what happens when you aren't obeying or aren't recognizing the fact that you have state to contend with. So in this particular scene that we will show in just a moment, we have a spacecraft. And where it is in the integration test lab. So you can see that picture that keeps jumping up there. And that picture, there we go. That picture is in the lab when we're delivering the spacecraft to the launch provider. So we're ready to go up and go to space. Now, on all of our satellites, we have a notion of what is time. What does time look like right now? Because when you send telemetry channels or you say, software logs, hey, this happened, you want to know what time it is. If you don't know what time it is, how can you tell how things relate together? Now, the problem with time is when this thing is up in space, you have to come up with a scheme for how time relates from the ground to the space. Otherwise, you will be lost in time. Is this going to work?
I think the Wi-Fi is a little bit rough in this room, but I'll keep this open on the site.
All right, so we'll just proceed without it. So we had a video, and what happens in this video, if you try to hit play, maybe it'll work.
It doesn't format as a video at all.
Okay, well, what happens in this video is you'll see us integrating during the test, and then surprise, surprise, the door of the payload opens in the middle of the integration bay. This is bad. Why is it bad? Because the door of the payload is not supposed to deploy until you get to space. It's not supposed to open in the integration lab. Let's just move on. And so, as a result, we had an issue with state. What happened was they were doing the integration and they forgot that this particular spacecraft never had time set. So its state was something like 1970 or actually I think it was 2000. And then when they went in and did the integration and set the time for launch, what happens? The door pops open. Oh no. And so what we had is we didn't reckon with the state of the spacecraft, and it jumped 26 years in the future, and it said 26 years is longer than the time I was supposed to wait to deploy the door. And as a result, the door opened in the lab, scared everyone, made our launch provider say, are you sure you want to launch this into space? And we said yes, because we know what the state is of the spacecraft, and we can tell you that we just jumped it 26 years in time, and it will not happen again until we're up in orbit. The other thing that we needed to be aware of is the trust we had in the team. This was one of the biggest lessons we learned on the project. You have to trust your team. We have another little tidbit about hidden state here, but you can see the various team members around here. And when we invested trust via the rule of two, via reviews, via discussing with people, we powered through software faster than I've ever seen working in traditional aerospace, because we let people be empowered to solve their problems and get spacecraft software that works. The perfect example of this was the day before delivery of our software and delivery of the satellite. We're sitting in a lab in Cal Poly, and the Texas team is sitting in a lab in Texas, and we're churning around, and we get a report from them saying, this one CubeSat is going into a reboot loop, and it just keeps rebooting over and over and over again. And so we tried to debug it, and after about 15 minutes, we concluded that only applies to one CubeSat. So we're going to go ahead and move on and finish testing and get our tests done so that we can prove this thing will work, meet our launch deadline, and get into space, right? But we trusted the team, and the Texas people had a different decision. They said, we're going to keep moving on this particular issue because we think it's critical. We're seeing it on our engineering hardware. And so they kept testing along through the day. We kept testing along through the day. And then, lo and behold, late at midnight, we popped this giant cannon of confetti because we delivered our software. We went home. We arrived for the day of the delivery on Sunday, and we had a pull request from the Texas team. Okay, they're giving us a pull request after the code freeze. And we look at the pull request and we say, oh, that line there, that would kill our cubes. Yeah, so what they had done is they had tested all day in Texas and figured out what commit caused this reboot loop. And when they sent us a pull request saying, hey, this is the thing we should take out, we looked at it and said, that's a cube killer bug. That will destroy every one of these 5 satellites in orbit. What had happened is a little hidden piece of state. When the CubeSat goes to sleep in safe mode and wakes back up later, it will wake up in safe mode. Safe mode triggers a sequence on boot that says, let's safe the radio. Make sure everything is in a quiescent state in the most vanilla, boring configuration so that we can talk to the ground. That sequence that tells the radio to go to safe ran before the sequence engine was initialized. And therefore, the sequence engine said, you can't run a sequence before we initialized. We should go to safe mode and reboot. Aha! Boot loop. Go to safe mode, reboot, go to safe mode, reboot. And so any spacecraft that rebooted in safe mode would be permanently stuck in safe mode in orbit. By trusting the team, the Texas team enabled us to get our tests done and prove that everything else on this software worked, while also we trusted the Texas team, enabling them to go through and figure out this cube killer bug, and the end result was well-tested software that met all of the checkboxes and proved all of the functionality, and the cube killer bug was removed in one of those releases that you saw on the first slide. By trusting the team, we solved both problems and let people self-select where they wanted to apply their expertise so that we converged on a working solution. So that brings us to the end of the talk. If you're interested in contributing, come chat with us. We'll be around SCaLE. We're happy to talk about this. And we have hopefully plenty of time for questions. We do love questions, so please ask some.
Questions? Yes.
What do you actually do to detumble your cubes?
Yeah, we have a B-dot detumble algorithm that was developed in Texas State. And we use our magnetokers for that, as well as our IMU and our magnetometers.
Did you mention to detumble them, are you using gyroscopes or motors or?
Oh, IMU.
IMU. Oh.
Oh, sorry.
So-
IMU. Go ahead.
An IMU is an inertial measurement unit that gives you roll, pitch, and yaw, and usually in several sets. So you have a magnetic reading and a gyroscopic reading, etc. You take that information, and then you take the information, then you power your magnetokers, which are just spindles of wire here in the spacecraft, and they produce a magnetic field. So if you modulate that magnetic field with respect to the magnetic field of Earth, you can effectively break the spin of the spacecraft so that it's spinning, and then it just kind of slows down into a stable pointing direction.
Solid state thingy that needs.
Yeah.
I had a question on your flight software. So let's say you cut a release on your flight software and you test it against your HIDL. Did you automatically upload the software on the HIDL, or were those like manually uploaded?
So, Yes, we do automatically upload each pull request to the hardware in the loop testing. So it wasn't just cutting a release, it was any change that came into the software was pulled into our CI system, run on a custom runner that was wired to one of these satellites. Up until the point in the mission where we had to stop the integration tests because the test harness itself had broken down, and then we started manually running them. Either way, we tested in the loop.
Yeah, so over here is an example of every single time someone pushes to a PR. So even if it's not like about to be merged in, the tests will run. And over here we have our integration instructions. Our linter, our unit tests are built in our integration tests. The integration test didn't specifically run on this guy, but I think it ran on this guy. Yeah, and so here's our integration tests suite. And then here's all of our tests. So we've got antenna deployer, burn wire. All of these are running like physically on a satellite unit.
Maybe I missed this, but what altitude are you guys putting the satellites, and what's the lifetime of how long they're going to be in space?
So we're launching out of the ISS. So we're at ISS orbit, which I want to say is like 473 kilometers, but don't quote me on that. Wherever the ISS is right now. And our orbital lifetimes right now, there's a lot of like solar flares and solar activity. So we calculated, I think, between 6 months and a year. The satellites with like the lead ballast was put to increase the flight lifetime by like 18 months because of kind of the weight on the satellites. Unfortunately, we had to remove the lead ballast because when we integrated with the satellite, the ballast was so heavy. We hit the maximum weight that you could for the satellite because we were like, oh, we might as well go to the maximum. And it turns out maybe nobody's ever done that because in the deployer, they check how many newtons of force you push. The deployer is like a spring, and you put these cubes in a box with a spring. It's a really expensive box with a spring. And so they want to make sure that the spring will be able to push your satellite out. And so the newtons of force were very strong because the lead is heavy and we're in gravity. And so it maybe would have worked on orbit, but we didn't want to risk it. And so, yeah.
And that's actually one of the things that I found really interesting. Sorry, I know you have a question. I didn't realize this, but the heavier your satellite, the longer it can orbit, because up there, it's all about the resistance, the friction that slows you down, and the heavier you are, the more momentum you have, so the longer it takes for this kind of background friction from solar flares and various other things to slow you down and deorbit you. So this thing without the lead would deorbit a lot faster than the original version that was a little bit too heavy for me to pick up with one hand.
You mentioned that you were using SD cards. I was just wondering how you kind of determine and calculate that the failure rate of something like an SD card is suitable for your use case, and also do you have any kind of like failure mitigations for something like an SD card? Basically hardware that's not really in your control, your development.
So I would like to clarify a little bit. In this particular CubeSat, I don't believe we have an actual SD card. We have a flash chip that has an SD card controller on the front. So from the perspective of software, it is an SD card. But from the perspective of hardware, it's an integrated circuit, which reduces the risk. That's an excellent question.
You mentioned there's a way to request a joke from the satellite. Is there documentation on that somewhere?
There will be. Keep an eye out on our GitHub or on our website, the Proofs Kit, Proofs Core reference. We're going to make a tool for radio amateurs so that you can send a fully formed packet up to the satellite. And our launch is on April 8th. Our deployment will be sometime in May. And then after that, we'll have the ability to ping the satellites.
I'm glad you asked that because I have a follow-up question to more comm stuff. Well, my first question is about the payload. So you mentioned you also have an S-band payload, or one of the CubeSats had one. Is that something you were able to test with like ham radio license as well, or okay? Are you able to use the same ground antennas, or did you have to subscribe to other stations? Was there a separate process?
Mm-hmm. Yeah, so a lot of our team does have like radio amateur license. Oh, yeah. Or is that, you have more question?
Yeah, yeah. So for the my next question is about the Zephyr F prime integration. Is that still actively maintained and supported, or and is there a contact for that?
Okay, so I'll answer the ground station, and then he'll answer F prime Zephyr. So a lot of our team does have like amateur radio licenses, so we're able to operate stuff. What we would often do during testing is we'd have 2 flight boards, and we'd use one as a ground station, so we had a ground station path through, and then we would have the other satellites and be the satellite. And so that's how we would test. Right now we're in the process of finalizing our ground station, so the Texas State team is going to have a ground station. The UC Santa Cruz team is going to have a ground station. We're friends with the Hawaii team who said we can also use their ground station. And so we have like university partners that we're going to be operating the satellites from. And so those are going to have like S-band capabilities and UHF LoRa capabilities for our LoRa radio. We are prioritizing LoRa UHF because that's most of our operational guide. Our satellites right now actually don't have S-band capabilities, even though we have an S-band radio, because right before integration we were running into issues with dynamic memory allocation, which is a big no-no with the S-band radio. And so those are going to be on the next satellites that are being handed off in May and launched in August. Those are going to hopefully have the S-band radio capabilities.
And then as for F prime Zephyr is a F prime community package that brings in Zephyr RTOS support. It is being actively maintained by several members of the community, one of them being the Open Source Space Foundation, one of them being the F prime team, and one of them being industry partners who are also running on top of F prime Zephyr. So right now, F prime Zephyr is actually a fairly stable RTOS integration.
I think you might have hinted to this, but how are you securing communications to the satellite?
Yeah, so we have a CCSDS compliant HMAC communication protocol. And so we're sending up security headers and footers that have a sequencing number to prevent repeat attacks. So first the satellite will check if the sequencing number has incremented, so no one's repeating commands. And then it will check an HMAC validation against the key that is stored securely on the satellite. And only authenticated packets will pass through the comm stack unless they're like a few ones that are reserved for radio amateurs, such as the tell joke command. The tell joke command can pass even when it's not authenticated.
So some of you who do cybersecurity may note that isn't a full cybersecurity protocol. We did a risk analysis of the satellite and determined that really the most dangerous thing somebody could do with this satellite in terms of the larger space community was to update new software and use the magnetorquers to kind of pilot it through the magnetic field. Very unrealistic, but we did make sure that the images that run are not something that somebody could update without having access to a separate imaging key. And so the images themselves are locked down. The authentication prevents unauthorized access, but the overall communication is still visible to the public. They just can't command or update software.
All right, so my question is, since you said that the ground station is still under active development, is that going to be open source if I want to have a satellite tracking ground station?
Absolutely. And there are also already open source ground stations. If you check out SatNogs, they've got a lot of resources for that as well.
Okay, and then quick, small second question. Are the jokes out of this world in a less literal way? Are they really that funny?
One of the jokes may or may not be the satellite is out of this world. I can either confirm or deny. You can, though, because the jokes are also open source, and the jokes are on GitHub. And actually, if you go to our code base, you can make a pull request to the jokes file and add a joke there. And I will probably approve you if your joke is funny enough. And maybe one of your jokes will be downlinked from space. So check out the proofs core reference. There's a QR code right there.
Yep. So you mentioned about the burn resistor as being a fun hardware hack. Could you say a few words about the measuring tapes? And do you have any other fun hardware hacks?
Okay, so this is something that gets me really excited because I'm not really a space guy, I'm a software guy, which is why when you asked how high we are in orbit, I'm just like, yeah, that number sounds right, because I do software. But the measuring tapes. Okay, so it turns out that the kind of antenna that you want on CubeSats are pretty much a metal bar that is about the width and length of a measuring tape. But the measuring tape has a really useful property in that it springs back, like that. And so many, many lower budget CubeSat teams just use measuring tapes. And if you come up here and look at the spacecraft a little bit later, if I don't destroy it entirely, you can look in there, and all we did was sand off, well, you sanded off the paint on the measuring tape where it connects, and otherwise we just left the measuring tapes in there because this is iconic lower budget CubeSat development.
Yeah. I think some other, or maybe we should keep going. Some other fun hardware hacks are our frame. A lot of people will do like a machine frame, which is very expensive. We did not do that. But we kind of had a jig. We had a 3D printed jig that we measured that was super accurate. And so when we ordered our frame, we were able to like measure against it. And so instead of having like a machine shop be very precise, we just ordered a bunch and measured and kind of like screwed them in. Because this is a little bit flexible when it's not properly screwed in order to get the right size. And yeah, we have a bunch of other fun hacks as well we can talk about later.
You have 5 satellites and I think 5 teams. Why not share satellites? And what was the reasoning behind each individually having your own? Was there separate payloads or what's going on there?
Yeah, so the first thing is that this kind of mission happened because we got an open source kit. And I'm sure you guys are big on the open source community. At least I really hope so. And one of the things you guys surely have encountered within open source is there's open source, and then there's open source with good documentation, and that people can recreate it and copy it and actually learn from it. And the proofs kit Cal Poly Pomoha had been developing for a while. They'd launched many satellites, but they wanted to take the next step and say, we want people to use it, and we want to make sure they can use it. And so by saying each university is going to individually make this open source kit, we can see how different stakeholders and different people are able to read this documentation, contribute to it, and like have different aspects. The other thing was we were also geographically separated, 5 universities in pretty different parts of the US, so it would have been really hard to make one satellite together. And these kits were also designed for a 1U. We just added the 2U, which is the unit of measurement. The small ones are 1Us. And so we got like 6 Us of space to launch satellites. And if we've got 6 Us of space, we're going to use all of them. And finally, I think I mentioned this a little bit earlier, but each of these satellites have like a different payload.
Curious to piggyback right a little bit. You have all of these different people with different skills, I'm guessing, or interests or sub-interests. How is it like as a leader when you're like, okay, we've got to build this thing? How do you determine, oh, this is the best configuration for us to work together?
Yeah, that's a really, really good question. And it was something that was really cool to find out in a team that was so asynchronous. And I think a big part of it is kind of this last slide that we were talking about, which is like, trust the team. We make big decisions together. We had like all of these plans and stuff. But when we give somebody a task, we trust that they can accomplish it, that they can design it, that they'll document it in a way that we'll be able to understand, and then make decisions that work for the satellite. And so, yeah, and so we were able to kind of iterate quickly and allow people to make decisions. And there's many ways to make a satellite. But we were able to find a way that worked for us and our team.
And I just wanted to plug here, because this is something that slipped my mind when we were talking about trusting the team. I'm a fairly seasoned flight software developer in aerospace. That's my day job. I'm not going to talk about it much because I'm here on behalf of Open Source Space Foundation. But trusting the team and trusting the leadership meant that I had to step into a role of not really being a leader, but being a follower, because I didn't have the time to volunteer for this apart from a few evenings and weekends. And so when I looked at the team, I was ready to be the leader because guess what? That's the role I normally take on. And then I noticed other people, Inez, doing the leadership role, and I'm like, oh, they've got this. I can just let this one go, which was a lot of fun for me, but it also made the team stronger because we let those people who are natural leaders and knew what they could contribute and how to orchestrate these people come together. So letting people step up, even if you have a higher experience level than them, gives them an opportunity, but also makes for a better team.
Question. So, real quick, as someone who's worked in CubeSat projects, both uni and professionally, I empathize with you folks who have stayed up late nights eating leftover pizza and what have you just to do testing. So kudos. So you've mentioned the value of open source development, componentization, things like the importance of iterative development. I even noticed in one of your slides you're using what appears to be semantic versioning for your code releases. Is that right? So these are all practices and approaches that like are very adaptable in software development, right? Have you applied similar approaches to hardware? And if so, what kind of pain points have you experienced?
I think we mentioned it a little bit, but like to expand on it, I really think like our lean development really came from the fact that the proofs kit was developed to be a lean hardware kit. We're a very, very cheap satellite when it comes to CubeSats, and that was because the hardware was designed to be iterated on quickly and was designed to be affordable for universities and manufacturable. And so we went through a lot of designs of the hardware throughout even these last 5 months because the hardware team was really leveraging these lessons of lean development. And so I would say like definitely that was like an important thing for us and something we learned from the hardware team.
So to clarify, I'm speaking more to the effect of, so you publish your software as open source, right? Do you do the same for your hardware? And if so, what does that look like? And how does that kind of diff between the approach you use for software versus hardware?
So to repeat the question, because the microphone wandered further back into the crowd, do we publish the hardware stuff as open source? The answer is yes. I believe Ines is showing us right now. And what kinds of approaches did we take to hardware development? So I don't think either of us are entrenched in the hardware team. I'll take a guess. Our hardware people did do revisions. They did do GitHub development, and they did check-ins and that sort of thing. And then I believe we've published our design schematics, the KiCad files or something similar. And KiCad is... Is it, oh, KiCad maybe is what they were trying to say. Okay, I'm a mess. Let's move past this. But it's available and is the documentation. And so theoretically, you can go to here, check it out, fab your own boards, build it, upload our software, and fly it if you can get a ride to space. Does that kind of answer the question? Okay, cool.
So you showed us that video of the gate swinging open, and that was an error resulting from some spacecraft state, and just not having a set handler for time on Zephyr. Is that something that is intentionally restricted in Zephyr, and is now a good time to ask about like how that was resolved?
Oh, so the issue was when you boot up our flight controller, we didn't have, I don't believe we have a real-time clock on here. And so it boots up in the year 2000. Zephyr does have a set time handler so that you can sync time. The problem was we booted up in one state. We do have a real-time clock. We had never set the real-time clock before. So the time was 2000. It knew the time was 2000. It tracked the state was 2000. Then we updated the time, and it was a delta of 26 years, which was longer than the 45-minute wait for deploying that door. And so it wasn't an issue of that stuff not being supported. It was the fact that we didn't preset the time before going into integration. And so we had this large time delta. So what is the solution? The solution is when you first boot up the board and first run the RTC, just set the current time. And then from then on out, you'll always have a reasonably close time modulo the clock drift of your real-time clock. Does that answer your question?
Thanks for a great talk, by the way. Question or two about power and thermal issues. Does it have a battery, or does it just turn off for 45 minutes every other 45 minutes? And also, maybe you could talk about, do you have to worry about this thing overheating?
So It does have a battery. If you, Ines here will show you, there's a 4-cell battery board deep in there. And so as it orbits, it will charge the battery from the outer planes. Now, that being said, one common problem with CubeSats of this size, I'm not going to say specifically for proofs because Ines can fill in the details, but power management is difficult because you only get so much power in from the solar cells, and so you charge your battery, but you should expect when you're orbiting in space to have some amount of downtime or quiet time where you can wait to charge. And then thermal management is another issue. In space, you don't have this atmosphere to conduct conduct heat away from your spacecraft. So you do have to manage both. Ines will tell you more of the details on how we approach that.
Oh yeah, and then also really quickly, I think you mentioned like, does it like sleep for 45 minutes? Our satellites don't ever sleep. But what we do for safe mode is that we turn off all the peripherals, and so all of the sensors are off. A lot of things that would gain power are off. The payload is off, and the only thing that is on is the radio, and it's just sending like health packets at a very like low rate, so that we can conserve as much power as possible. And basically the idea is if an anomaly happens, we want minimal systems running because who knows what that anomaly is from. So that 45-minute wait is just just hang out in the satellite and don't do anything until the 45-minute wait, but the satellite's still on and it's running. And then after the deploy, we'll turn the radio on and we'll deploy the antennas and all of that fun stuff. And then once the radio is on, then we'll start like sending out packets. And then in terms of the heat things, some satellites will have battery heaters, some satellites will have heat sinks. Because our satellites are pretty simple in what they're doing and they're not emitting a ton of heat, but also we like calculate that we didn't need battery heaters specifically for a battery, we actually don't have any active thermal components on our satellites, just passive based on kind of the satellite design. In the past, the proofs kit has had battery heaters, but the thermal team decided that wasn't essential for this launch. And keeping it simple is pretty important for us.
So one more thing. One place that CubeSats run into a lot of power and thermal issues is when they ship a big computer like something capable of running Linux. We've got an RP2350 in here. So it's a much smaller, much deeper embedded processor and a whole lot smaller to work with, which is why you've heard we had some RAM problems that we alluded to. But the importance of that small processor is it keeps the heat output and the power consumption of your primary computer very small. One thing you might do, and I see a lot of CubeSats do in the field, is they have a small computer like the RP2350 that runs the satellite, and then they have a payload computer that they can turn on and off when they want to do much more compute-intensive things. We don't have that in the proofs design because it's not required to meet our mission parameters, but that is another option in the space.
It sounds like at the end of your talk, you guys were kind of down to the wire and came across a boot loop from Texas Tech or University of Texas. And I was wondering how that didn't get caught in your hardware in the loop tests, and if there was any key takeaways on how you structure your tests or how you would structure your tests in the future from realizing that that wasn't caught, or was it caught? I don't know.
Thank you for asking that question, because Ines told me I should talk about that during the slide and it slipped my mind. So why didn't we go into safe mode in any of our tests? The answer is we did go into safe mode. The problem was we never bothered to upload the final safe mode sequence. And so we would go into safe mode but never try to run anything and therefore not invoke this problem. So what recommendation can I give you about doing better tests? Make sure that your system is in a complete state and upload all the necessary files, even if they're placeholders or reasonably small, so that you have as close to flight as expected.
Another limitation of our integration tests is that if we ever did like a reboot during integration tests, the connection to the integration tests would fail, and it'd be really hard to automatically have it like catch it back up again. And so we didn't have things like, oh, what happens when this anomaly loops, just because of the limitations of our testing software. We also didn't have tests that like run everything on the satellite at once. We reserved all of those tests for like integration testing at the end and like operational testing, because that was just easier. But definitely a lesson learned is to do stuff like that, those states that you're not testing into integration tests, way more often.
I have two what I think are quick questions.
what happens at the end of the life cycle of the cube? Like, are they reusable, or does it get burned up in the atmosphere? What is happening to it? And how do I get one of those cute little plushies?
Aww. So the FCC says that your satellite has to deorbit within 5 years for like a regular satellite license. Most CubeSats don't need like propulsion or anything to do that because they're so small and they don't have enough momentum. And so within 5 years, they'll just go slower and lower and lower until they burn up peacefully into the atmosphere. And so that's what's going to happen to all of our satellites well within 2 years because of the weight and just the solar flare activity level right now. And then for the CubeSat plushies, I think there's a website called like makeyourplushie.com or something. And our systems lead, he sent a picture of one of our 1Us to that website. You can draw like anything and they'll turn it into a plushie. So they turned our satellite into a plushie and then they ordered a bunch. We are taking pre-orders. I think we ordered like a few hundred or 100 or something and they all sold out. And so now in order to do like another order, we have to get a bunch of pre-orders because it's kind of expensive because they're like $40 each. And if we're ordering like 100, it's like several $1,000s. But if you're interested, I'll add you onto the list and hopefully within like a year or something, we'll have enough people for another order.
So the satellite will fall down within 5 years, but you said it will last maybe to a year from the friction. Will it be operational through that whole year, or will the batteries die during that time, or what you expect it to run until it falls down?
Yes, we believe it will run until it falls down. Modulo space is hard. And so things can happen, solar flares, all sorts of stuff. We could get hit by a piece of space junk. And to answer your earlier question that you asked me in the hall, these aren't going to become space junk because they will deorbit and burn up. And the reason that the CubeSat licenses have these durations to deorbit is because the amount of stuff in space is growing, and NASA is actively trying to push for a model where things have a timeline to deorbit to keep our skies clutter-free.
And also in terms of like losing power, that's partly why we have safe mode. So if the satellite is like draining power, the solar panels will hopefully become power positive and recharge the satellite. And so we'll turn everything off to like make sure the satellite is able to get to like a healthy power.
Thank you for your wonderful questions, and thank you for this wonderful presentation. Thank you.
If you guys want to come up and touch the satellite, be very careful, but we can have that. And if you guys have any more questions.
Don't kick it like I did.
Don't kick it.